Somewhere out there, beyond the pull of our sun, past the farthest planets, and deep into the abyss of interstellar space, lies the question that could define the future of our species. Will we ever leave our solar system? This isn't just a scientific query. It's a test of imagination, of endurance, of cosmic ambition. It's the next chapter in a story that began the moment we first looked up and wondered what lies beyond the stars. For centuries, Earth was the boundary. Then we leapt into orbit, to the moon, and sent machines to explore the outer planets. But the solar system itself, the entire realm governed by our star's gravity, still contains us. It holds us like an invisible cage. And now, the question becomes more urgent: can we ever break free? Let's be clear, our solar system is massive. It stretches far beyond the orbit of Neptune, encompassing icy comets in the Kuiper belt and mysterious objects in the Oort cloud. Escaping it isn't just about distance, it's about escaping the sun's gravity, radiation, and influence. It's about venturing into a realm where no spacecraft has gone manned, where communication delays become hours, and where we would be truly alone, untethered from our home star for the first time in history. Yet, we've already taken the first step. In 1977, 2 robotic emissaries, Voyager 1 and 2, were launched into the cosmos. Decades later, Voyager 1 became the first human-made object to cross into interstellar space. But it took over 40 years just to get there. And it carries no people. No colony. No return path. Just a golden record and a whisper of our existence. So, can we do better? Can we build the propulsion systems, the life support, the shielding, and the knowledge to one day send human beings beyond the reach of our own star? This question doesn't just belong to scientists. It belongs to all of us. It touches on philosophy, destiny, survival, and the boundless human urge to explore. Because to leave the solar system is to enter the cosmic ocean. It's to finally answer the call of the stars, not as myth, but as mission. Some will argue it's impossible. The distances are too vast, the technology too primitive, the risks too great. But others see those same facts and feel the opposite: challenge accepted. In this journey, we'll dive into every aspect of this monumental question. From the scientific definitions of our solar system's edge to the wildest propulsion concepts ever imagined. From the biological hurdles of deep space to the philosophical motivations for ever going at all. We'll examine the limits of physics, the dreams of futurists, and the fragile nature of human biology. We'll ask whether it's really about us going at all, or whether our intelligent machines might make the leap before we do. And most of all, we'll ask, if the stars are within reach, what would it take to actually touch them? Because the stars are not just distant lights. They are destinations. And this story, our story, is about whether we'll ever find a way to reach them. To understand what it means to leave our solar system, we must first understand what lies beyond it. The moment a spacecraft escapes the gravitational influence of our sun and crosses the heliopause, the outermost boundary of the solar wind, it enters a realm so vast, so empty, and so unexplored that even the term, space, seems inadequate. This is interstellar space, the vast expanse between stars. It is not a complete vacuum, though it comes closer to one than almost any place we know. Here, matter is sparse, just a few atoms per cubic centimeter, floating in a sea of cosmic rays, magnetic fields, and cold dust drifting between ancient stars. In every direction from our solar system lie other stars, each one a distant sun, most of them orbited by their own families of planets. The Milky Way galaxy, our home, contains an estimated 100 to 400 billion of them, each separated from the next by light years of darkness. Some of these stars are solitary, like our sun. Others are binary or even part of complex star systems. Some burn hot and fast, dying in cataclysmic supernovae. Others flicker dimly for trillions of years. These stellar furnaces create the elements that make life possible, and their endless variety suggests a universe teeming with possibility. Orbiting many of these stars are exoplanets, worlds beyond our solar system. The first confirmed discovery of an exoplanet around a sun-like star came in 1995. Since then, we've cataloged over 5,000 of them, with thousands more awaiting confirmation. Some are gas giants larger than Jupiter, whirling in tight orbits scorchingly close to their stars. Others are rocky Earth-like planets that sit in the habitable zone, where temperatures might allow for liquid water, a key ingredient for life as we know it. There are planets covered in clouds of methane, worlds with double sunsets, planets that orbit pulsars and are bombarded by intense radiation, and others shrouded in perpetual darkness. Some are tidally locked, with one side forever scorched by daylight and the other eternally frozen. Some may have massive moons, global oceans, or even atmospheres similar to Earth's. Every year, our detection methods improve, from transit photometry to radial velocity to direct imaging, revealing not just the existence of these worlds, but hints about their compositions, atmospheres, and perhaps, someday, even biosignatures. And beyond all that, beyond the known planets and stars, there lies the unknown. We may one day encounter rogue planets, lonely wanderers that don't orbit any star at all. These orphaned worlds, ejected from their systems during violent gravitational interactions, drift silently through interstellar space. Some might still retain heat in their cores, or even subsurface oceans sealed beneath icy crusts, potential havens for life hidden from view. In the deepest voids between the stars, we may also pass ancient remnants of the galaxy's violent past, neutron stars, black holes, the echoes of supernovae. Invisible until you're too close. Dangerous. Mysterious. Beautiful. Yet even all this rich tapestry of stars and planets and cosmic wreckage, is just our immediate neighborhood. Just our galaxy. Beyond the Milky Way lie billions of other galaxies, each home to billions of stars. And beyond those, the structure of the universe itself stretches into incomprehensible distances, shaped by dark matter, dark energy, and forces we don't yet fully understand. But to even begin approaching these distant wonders, we have to escape the very thing that binds us, the gravitational grip of our sun. To leave the solar system is not just to cross a distance, it's to change our place in the cosmos. To take a step from being planetary explorers to becoming a space-faring species on a galactic scale. And it all begins with understanding not only what we want to leave, but where we hope to go. Most people think the solar system ends at Pluto, or maybe at Neptune, the last officially recognized planet. But in truth, the solar system is far larger, and far stranger, than most imagine. It doesn't have a hard outer edge like a fence or a wall. Instead, it fades away gradually, layer by layer, until eventually the sun's influence becomes too weak to matter. And understanding where the solar system ends is crucial to knowing what it means to truly leave it. The first and most important concept is the heliosphere, a vast, invisible bubble that the sun inflates around itself. This isn't a bubble made of matter, but of charged particles, the solar wind, a stream of plasma constantly flowing out from the sun in all directions. This wind creates a protective cocoon that deflects most of the cosmic radiation that comes in from interstellar space. It's like an atmospheric shield for the entire solar system. Within this sphere, the sun dominates everything, its gravity, its light, its magnetic fields. All the planets, all the moons, all the asteroids and comets we know reside within this zone. But even this enormous structure isn't infinite. Eventually, the solar wind slows down as it pushes up against the thin gas and dust of interstellar space. That point, where the solar wind begins to lose its strength, is called the termination shock. It's like the sun's wind hitting a cosmic speed bump. Here, the particles abruptly slow down and heat up, forming a turbulent, chaotic region. This area, stretching for billions of kilometers, is the beginning of the end. Farther out lies the heliopause, the true outer boundary of the heliosphere. This is the point where the solar wind no longer has the strength to push back against the pressure of the interstellar medium. In other words, it's the place where the sun's influence is finally balanced, where its breath, so to speak, gives out. Beyond the heliopause, the environment changes completely. The magnetic fields are no longer solar. The particles are no longer from our sun. Space becomes truly interstellar. It's this crossing, the heliopause, that Voyager 1 achieved in 2012. After 35 years of travel, it became the first human-made object to leave the heliosphere and enter interstellar space. But even this isn't the final frontier. Far beyond the heliopause lies a region so distant that even our most ambitious spacecraft will take thousands of years to reach it, the Oort cloud. Unlike the heliosphere, which is defined by energy and magnetism, the Oort cloud is a collection of objects, icy remnants from the early solar system. It forms a vast spherical shell around the Sun, stretching perhaps up to 100,000 astronomical units, AU, from the center. For context, Earth is $1 from the Sun. Neptune is about $30. Voyager 1, the farthest spacecraft, is only a little beyond $160. The Oort cloud? It begins around $2,000 and might continue for tens of thousands more. This cloud is thought to contain trillions of comets, scattered across space in all directions. Occasionally, a passing star or gravitational disturbance may knock one loose, sending it plunging toward the inner solar system. But mostly, it's silent. Cold. Forgotten. What's important here is that even at the edge of the Oort cloud, the Sun's gravity still exerts a pull. Faint but real. A spacecraft would still technically be in orbit around the Sun. To truly leave the solar system by the strictest definition means to escape the Sun's gravity entirely. To reach a velocity where one is no longer bound, not even loosely, to its pull. So where does the solar system end? It depends on who you ask. If you go by magnetic influence, it ends at the heliopause. If you go by the last physical objects, it ends at the edge of the Oort cloud. And if you go by gravity, it never really ends at all, until something breaks free. That's what makes the idea of leaving so complicated. We may already have touched interstellar space. But have we truly escaped the solar system? To truly grasp what it means to leave the solar system, we have to confront a paradox. There's no single, universally agreed upon point at which we can say, definitively, we're out. Unlike crossing a border on Earth or stepping through a doorway, space is not so clearly defined. It's layered, like an onion, with different kinds of influence fading gradually rather than cutting off sharply. And that makes the idea of leaving far more complicated than it first appears. Let's begin with the concept of crossing the heliopause. This is a physical, measurable threshold where the solar wind, the constant stream of charged particles emitted by the Sun, collides with the interstellar medium, the incredibly thin gas and dust that fills the space between stars. Inside the heliopause, everything is dominated by the Sun's particles and magnetic field. Outside of it, those conditions change. The interstellar medium takes over. It's colder, denser, and has a different magnetic structure. When Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2018, they entered a place where the Sun's energetic particles no longer shaped their environment. From a physics standpoint, that was a major milestone. A true entry into interstellar space. But then there's gravity. The Sun's gravitational pull doesn't stop at the heliopause. It doesn't even stop at the Oort cloud. In fact, it technically never ends. Gravity, unlike light or wind, doesn't have a finite reach. It weakens with distance, yes, but it always exerts some influence. Even at a distance of tens of thousands of astronomical units, where the Oort cloud is believed to exist, the Sun still has a gravitational claim on passing objects. So if we define leaving the solar system as escaping the Sun's gravity completely, the bar is set much higher. Let's put it in numbers. The escape velocity from Earth is about 11 kilometers per second. But to escape the Sun's gravity from Earth's orbit, you need to be going around 42 kilometers per second, and even more if you're farther out, because as your orbit slows, you need an extra push. Voyager 1 is moving fast, around 17 kilometers per second, but it's still technically within the Sun's gravitational influence. However, because it's not orbiting anything and won't come back, some scientists still consider it unbound, a kind of gravitational ghost, forever drifting outward. That's where the definitions begin to blur. Is being unbound enough? Is a probe still within the solar system just because it could theoretically fall back millions of years from now if slowed? Or is the fact that it will never return enough to call it free? There's also a philosophical angle. For most people, the idea of leaving the solar system conjures up something more than numbers. It suggests a kind of existential detachment, a moment when we are no longer passengers of our sun. When we no longer rely on its energy, no longer think of its orbiting planets as the entirety of our home. Perhaps leaving the solar system isn't just about crossing physical boundaries, it's about entering a new frame of reference. When we start navigating not by planets, but by stars. Even now, Voyager's antenna points back toward Earth, still sending signals to the deep space network. It's out there, yes, but it's still with us in a profound way. The moment we send something, or someone, so far that Earth becomes a fading dot on a map they no longer follow, that might be the true departure. So, what counts as leaving? Crossing the heliopause? Escaping gravity? Becoming truly independent of the sun? There is no final answer, and perhaps there never will be. But maybe, just maybe, leaving the solar system isn't about passing a boundary at all. Maybe it's about crossing a threshold in our minds, realizing that the solar system is not the limit of where we can go, but the starting line. In the vast silence of space, far beyond the last planets, two faint signals continue to drift back toward Earth, messages from the edge of the known. These signals come from Voyager 1 and Voyager 2, the only human-made objects to cross the heliopause and enter interstellar space. Though they are no bigger than a small car and powered by nothing more than radioactive decay, they represent something enormous, the first emissaries of humanity to step into the void beyond our sun's domain. Launched in 1977, the Voyager spacecraft were originally designed for a grand tour of the outer planets. Voyager 2 lifted off first, on August 20th, followed by Voyager 1 on September 5th. Their mission was ambitious but limited in scope, to explore Jupiter and Saturn and, if possible, push farther. Thanks to a rare planetary alignment that occurs only once every 176 years, the spacecraft could use a technique called gravity assist, slingshotting around planets to gain speed and redirect their trajectories outward, deeper into the solar system. Voyager 1 took the faster route, reaching Jupiter in 1979 and Saturn in 1980. It captured groundbreaking images, swirling storms, volcanic moons, intricate ring systems. But after its Saturn flyby, it veered upward out of the ecliptic plane, the flat disk where most of the solar system's planets orbit, on a path that would eventually take it beyond the sun's influence. Voyager 2, meanwhile, went on to achieve what no other spacecraft has done. It visited all four gas giants, Jupiter, Saturn, Uranus, and Neptune. It revealed new moons, discovered strange magnetic fields, and observed previously unseen phenomena like the hexagonal storm at Saturn's pole and the icy geysers on Neptune's moon Triton. After their planetary missions ended, both Voyagers transitioned to something far more audacious, an interstellar mission. Their new goal was not just to travel farther, but to become the first objects to escape the solar wind, cross the heliopause, and enter the uncharted space between the stars. Voyager 1 achieved this on August 25, 2012. The crossing was not dramatic. It wasn't like a ship passing a border checkpoint, but the data it returned showed a sharp drop in solar particles and a corresponding increase in galactic cosmic rays. That was the sign. Voyager 1 had entered a new domain, the interstellar medium. Voyager 2 followed 6 years later, crossing the heliopause on November 5, 2018. Each spacecraft provided humanity with its first direct measurements of the interstellar environment. And yet, despite being billions of kilometers from Earth, the Voyagers are still talking to us. Their signals are faint, taking over 20 hours to reach Earth and traveling at the speed of light. But they carry priceless data, measurements of particle densities, magnetic fields, and cosmic radiation in a region no probe has ever visited. What's even more poetic is what they carry with them. Each Voyager holds a golden record, a copper phonograph disc etched with the sights and sounds of Earth, greetings in 55 languages, music from Bach to Blind Willie Johnson, sounds of whales and laughter, and images of life on our planet. They were curated by a team led by Carl Sagan, designed as a time capsule, or a message in a cosmic bottle. If ever found by another civilization, They would serve as a cosmic handshake, an introduction to who we are. But these messages are not meant for us. They're meant for the unknown. For the distant future. Long after the Voyagers fall silent, and that day is coming, likely sometime in the 2030s when their power runs out, they will continue to drift, unbound by any orbit, across the galaxy. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of another star. In 300,000 years, Voyager 2 will do the same. They will wander through the Milky Way, perhaps forever, as the last traces of a civilization that dared to look outward. They are, in every sense, our first interstellar ambassadors. Not because they represent conquest or colonization, but because they represent curiosity, hope, the desire to connect, the urge to reach out, even if no one is listening. And though they are uncrewed, unthinking machines, the Voyagers have already achieved what generations of science fiction could only imagine. They have taken us beyond the sun's protective shell, into the unknown. They are a whisper from Earth, traveling eternally toward the stars. Despite the remarkable achievements of the Voyager missions, they also highlight a sobering reality. Space is big, and we are slow. In fact, one of the most daunting obstacles to leaving our solar system is simply how long it takes to get anywhere. Even with our fastest spacecraft, we're crawling through the cosmos at a snail's pace compared to the vast distances involved. Let's consider Voyager 1 again. It launched in 1977 and only crossed into interstellar space in 2012, 35 years later. And even then, it had not truly left the sun's gravitational influence, nor had it come anywhere near another star. In over 4 decades, Voyager 1 has traveled around 160 astronomical units from the sun. That's roughly 24 billion kilometers, an enormous number by human standards, but tiny on the galactic scale. To put that in perspective, a single light-year is nearly 63,000 times farther than the distance from Earth to the Sun. Voyager 1 is only a little over 0.05% of 1 light-year away. Let that sink in. More than 40 years of travel, and we've only covered a fraction of 1% of the distance to the nearest stars. Voyager 1 is moving at around 17 kilometers per second relative to the Sun. That's fast. Much faster than a bullet, or a jet, or anything we experience on Earth. But in space? It's still incredibly slow. At that speed, reaching Proxima Centauri, the nearest star to our own at just over 4.2 light-years away, would take over 75,000 years. That's longer than the entirety of recorded human history. Longer than modern humans have even existed. And Voyager is still one of the fastest objects we've ever launched. Most spacecraft, especially those bound for planets closer to Earth, move far more slowly. Mars rovers, lunar orbiters, even missions to the gas giants, none of them come close to the speeds needed for meaningful interstellar travel. Why are we so slow? The simple answer is energy. Accelerating a spacecraft to even a tiny fraction of the speed of light requires an enormous amount of fuel, propulsion, and engineering. Every extra kilogram of weight adds exponential demands. Every acceleration brings additional constraints on stability, shielding, power generation, and more. There's also the problem of drag, not from air, but from interstellar particles. At very high speeds, even the thin dust of space becomes dangerous. A tiny grain of sand impacting a spacecraft moving at a significant fraction of light speed would hit with the force of an explosive. Protecting against that kind of hazard becomes harder the faster you go. And then there's logistics. The faster a craft moves, the more precise its navigation must be. The more power its systems require. The more robust its communications need to be. Voyager can take 20 hours to send a signal back to Earth. Something halfway to Proxima Centauri could take years for a single round-trip message. And during that time, the position of stars, planets, and hazards will have changed. Timing becomes critical. Accuracy becomes everything. The speed problem doesn't just make travel slow, it also makes missions risky. The longer a journey takes, the more things can go wrong. A piece of debris, a software glitch, a power failure, or a system's freeze can ruin an entire mission decades in. And for humans, the challenge is even greater. How do you sustain life for thousands of years in deep space? How do you protect against radiation, cosmic rays, and psychological isolation? How do you build a ship that won't fail for generations? Even our ambitious future concepts, like laser-accelerated probes or nuclear propulsion, only begin to scratch the surface of what's needed to make interstellar travel feasible within a human lifetime. For now, we're limited by the same basic constraints that have shaped space travel since the dawn of the rocket age. We can go fast, but only for short bursts. Sustained high-speed travel through space remains just out of reach. So, the speed problem isn't just a hurdle. It's the wall that stands between us and the stars. Until we figure out how to dramatically increase our velocity, or invent entirely new methods of propulsion, we're stuck moving through the universe at a pace that makes human interstellar travel seem more like myth than mission. And yet, the Voyagers are still moving. Still heading outward. Still defying the silence. Their slow drift through the cosmos reminds us of one thing. Even if the journey is long, it has already begun. If speed is one of our greatest limitations, then distance is its unforgiving partner. Space isn't just empty, it's colossally vast. Even the closest stars are so far away that they challenge our intuition, our engineering, and our patience. The very nearest star system to our own, Alpha Centauri, and its smallest member, Proxima Centauri, sits at a distance of just over 4.24 light-years from Earth. That might sound manageable. After all, 4 is a small number. But a light-year is not. A single light-year is the distance that light, traveling at nearly 300,000 kilometers per second, covers in one Earth year. That's nearly 9.5 trillion kilometers, or about 5.88 trillion miles. Multiply that by 4.24, and you're looking at nearly 40 trillion kilometers to reach Proxima Centauri. 40 trillion kilometers. Let's try to put that into perspective. If Earth were the size of a basketball, the Moon would be a tennis ball about 7 meters away. Mars might be a golf ball in the next room. Pluto would be a marble down the block. But Proxima Centauri? It wouldn't even be in the same city. It would be thousands of kilometers away. That's how spread out space is. Even neighbors are separated by gulfs so vast, they almost become conceptual rather than physical. Let's return to Voyager 1, currently the farthest human-made object from Earth. After more than 40 years of travel, it has gone roughly 24 billion kilometers, or about 0.0025 light-years. At that rate, it would take over 17,000 years just to reach the distance to Proxima Centauri, if it were even going in the right direction, which it's not. Suppose we designed a theoretical spacecraft that could travel 100 times faster than Voyager 1, a huge leap by today's standards. Even then, the trip would take 170 years. That's 2 lifetimes of continuous flight. And that's just to get to one star. The second closest star is even farther, and the rest are exponentially more distant. Now imagine sending humans. They need food, water, oxygen, protection from radiation, psychological support, and some means of maintaining life for potentially centuries. And if we sent uncrewed probes instead, they'd still need to function reliably across many decades or even millennia, through the harshest environment imaginable, without a single technician to repair them. Of course, the Alpha Centauri system is interesting not just because it's close, but because Proxima Centauri b, a planet orbiting Proxima Centauri, lies in the star's habitable zone. That means it's at a distance where liquid water could exist on its surface. It may be rocky, like Earth, and it may, just may, have the ingredients for life. This tantalizing possibility makes it the most logical target for humanity's first interstellar mission. But even then, knowing it exists and reaching it are 2 entirely different things. And remember, 4.24 light-years is close by galactic standards. The Milky Way galaxy itself is over 100,000 light-years across. The center of the galaxy? About 26,000 light-years away. If we ever hope to explore even a fraction of our galaxy, we're not just talking about technological evolution, we're talking about a complete transformation of what it means to travel, to explore, and perhaps even to exist. But everything has to start somewhere. And Proxima Centauri is that starting point. A distant ember flickering just beyond reach, daring us to find a way. When we hear the term lightyear, it's easy to let the mind glaze over. It sounds more like a unit from science fiction than a real measurement. But a light year is very real, and understanding its scale is one of the most sobering steps in grasping the true difficulty of interstellar travel. Let's strip it down to its meaning. A light year is the distance that light, traveling at about 300,000 kilometers per second, can move in a single Earth year. That's 9.46 trillion kilometers, or about 5.88 trillion miles. Now here's where the shock sets in. Nothing we've ever built, nothing we've ever launched, comes remotely close to that speed. Not even a tiny fraction of it. Voyager 1, our fastest interstellar traveler, is cruising along at 17 kilometers per second. That's fast enough to circle the Earth in under 25 minutes, but in cosmic terms, it's crawling. At that pace, Voyager 1 would take about 17,600 years just to travel 1 light year. 1. The closest star, Proxima Centauri, is over 4.2 light years away. That's more than 75,000 years of travel for a probe already moving faster than any human-made object ever has. To really grasp this, imagine you had the power to freeze time and watch a line slowly being drawn across a black canvas, each millimeter a day of travel. For 48 years, the line would barely leave the starting point. You'd zoom in, wait, watch, and still it would not even begin to etch out a meaningful distance toward another star. That's the scope of the challenge. A journey of trillions of kilometers, made in slow motion over geological time. Let's try another comparison. If Earth and Proxima Centauri were two cities, and light was a jet plane flying between them in 4.2 hours, then Voyager would be a snail crawling along the same route. It wouldn't arrive in hours, or days, or years. It would take millennia. Even if we could somehow build a spacecraft that travels at 10% the speed of light, it would still take over 42 years to reach Proxima Centauri. That's within a human lifetime, sure, but getting to that speed would require staggering breakthroughs in energy, propulsion, and shielding. It's not something we can just scale up with current rockets. We're talking about re-engineering the entire concept of motion in space. And yet, despite the mind-numbing distance and the ridiculous travel times, it's still hard not to dream. Because even though 1 light year is an ocean, it's also the first ocean. The first step. If we could solve that, just that, we would crack open the door to the stars. 1 light year may sound like a number. But in practice, it's a wall. A wall built not of steel or stone, but of raw distance, of relativistic limits, of the reality that our species evolved to live and die within 1 small planetary cradle. And the fact that we even talk seriously about crossing that wall is a testament to something deep in us, a refusal to be confined. We are creatures of 1 star for now. But the stars, all of them, await us, 1 impossible light year at a time. Chemical rockets have carried us farther than any other technology in history. They've taken humans to the moon, sent rovers to Mars, and flung robotic explorers toward the outer planets and beyond. Every spacecraft humanity has ever launched began its journey on a column of chemical fire. But for all their triumphs, there's one cold and unavoidable truth: chemical rockets will never take us to the stars. The fundamental problem lies in their limitations, limits not of ambition, but of physics. Chemical rockets work by storing fuel and oxidizer, usually in the form of liquid hydrogen and oxygen or other propellants, and then igniting them in a combustion chamber. The explosion produces high-pressure gases that are funneled out of a nozzle, creating thrust in the opposite direction, according to Newton's third law. This method is effective for escaping Earth's gravity and operating within our solar system. But it's deeply flawed when it comes to interstellar travel. The main issue is specific impulse, or ISP, a measure of how efficiently a rocket uses fuel. Chemical rockets have an ISP of around 300 to 450 seconds, depending on the type. That may sound technical, but it boils down to this: you need an enormous amount of fuel to generate even modest changes in velocity. And when you're dealing with trillions of kilometers, that kind of inefficiency becomes catastrophic. If you wanted to accelerate a spacecraft to just 10% the speed of light using chemical propulsion, the fuel-to-payload ratio would be astronomical. You'd need more mass and fuel than exists on Earth, literally. This is where the Tsiolkovsky rocket equation comes in, a formula that governs how much velocity, or delta V, a rocket can achieve based on its fuel mass and engine efficiency. The equation exposes a brutal exponential relationship. To go a little faster, you need a lot more fuel. To double your speed, you might need 10 times the fuel. To reach a significant fraction of light speed, you're in the realm of absurdity. Even when we optimize chemical propulsion to its absolute limits, we're still talking about speeds that are utterly inadequate for interstellar travel. The Saturn V, the mighty rocket that took humans to the moon, could reach a velocity of about 11 kilometers per second, enough to escape Earth's gravity, but not even remotely close to what's needed for deep space journeys. Even the New Horizons spacecraft, one of the fastest ever launched, travels at around 14 kilometers per second. At that rate, reaching Proxima Centauri would take over 80,000 years. The problem compounds when you consider that a spacecraft doesn't just need to accelerate, it also needs to decelerate at the destination. If you use all your fuel to get there, what's left to slow you down? Without the ability to stop or adjust course, you're essentially throwing a rock across the galaxy and hoping it hits something meaningful. Another massive limitation is payload capacity. The more fuel you carry, the heavier your rocket becomes. But the heavier it becomes, the more fuel you need just to lift that fuel. It's a vicious cycle. Every kilogram of cargo, whether it's scientific instruments, a communication system, life support, or shielding, adds to the demand. And when you're aiming to send a crew, not just a probe, the payload grows exponentially. You need water, food, oxygen, radiation shielding, artificial gravity solutions, and systems redundancy. With chemical rockets, each of these necessities becomes a massive penalty in mass and complexity. Even within our solar system, these limits are a challenge. That's why missions to the outer planets take years or even decades. It's why we rely on gravity assists, using the pull of planets to boost our speed, because we can't simply burn more fuel to get there faster. We're squeezing the absolute maximum out of every drop of propellant, and still, we're crawling. Then there's cost. Launching mass into space is brutally expensive. Every kilogram costs tens of thousands of dollars just to reach low Earth orbit, let alone escape velocity. With chemical propulsion, we're paying dearly to achieve inches in a race measured in light years. On top of that, there are technical constraints. Chemical propulsion creates extreme heat and vibration, placing huge stress on materials and systems. The need to store volatile fuels safely over long durations, potentially decades or centuries, presents immense engineering challenges. Tanks can degrade. Seals can fail. Propellants can boil off or become unstable. In short, chemical rockets are not built for the long haul. Let's imagine a hypothetical scenario. Suppose you wanted to build a chemical rocket capable of sending a human crew to Proxima Centauri and back. You need a spacecraft that can not only reach a meaningful percentage of light speed, but also decelerate, operate for decades or centuries, sustain life, and then return. The size of the rocket required would be so absurdly massive, probably larger than a small moon, that it could never be launched from Earth, let alone constructed with current technology. And even if you built it in orbit, the amount of fuel needed would make it functionally useless. The rocket would collapse under its own ambition. That's why most serious interstellar mission proposals don't even consider chemical propulsion. It's a dead end for deep space. It served us well for getting off the ground, into orbit, and exploring nearby worlds. But for the stars? It's like trying to cross an ocean with a canoe. The good news is, we've known this for decades. Scientists and engineers have long realized that new forms of propulsion are essential if we're ever going to leave the sun's domain in any meaningful way. We need methods that go beyond combustion, systems that use nuclear power, electromagnetic forces, or even the fabric of spacetime itself. We need to rethink motion itself. In the grand journey from Earth to the stars, chemical rockets were the first steps, giant steps, to be sure, but steps that have taken us as far as they can go. Now, if we hope to continue, we must let go of fire and fuel and embrace the next revolution. If chemical rockets are the flint and tinder of space exploration, nuclear propulsion is the promise of fire, raw, potent, and orders of magnitude more powerful. While traditional rockets have brought us to the edge of the solar system, the energy density of chemical fuel is simply too low to push us to the stars. Nuclear propulsion offers a solution not through a small improvement, but a profound leap, a shift in how we think about motion in space. Let's begin with nuclear thermal propulsion, one of the more mature and realistic ideas in this domain. The concept is relatively simple in theory. A nuclear reactor heats a lightweight gas, typically hydrogen, to extremely high temperatures. This superheated gas then expands rapidly and is expelled through a nozzle, producing thrust. Unlike chemical rockets, which rely on chemical energy stored in the fuel itself, nuclear thermal engines use the heat from fission reactions to energize a propellant, allowing for far greater specific impulse, a measure of fuel efficiency. A nuclear thermal rocket could potentially double or even triple the efficiency of a chemical rocket. That translates into faster travel, higher payload capacity, or both. In a future crewed Mars mission, for instance, a nuclear thermal system could cut travel time from 9 months to 3 or 4, drastically reducing exposure to radiation and other risks. The technology isn't just theoretical. In the 1960s and 70s, the United States developed and successfully tested a series of nuclear thermal rocket engines under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. These engines demonstrated impressive performance, and the tests confirmed the feasibility of building nuclear-powered spacecraft. But the program was shelved, not for technical reasons but fallout from Cold War tensions, shifting NASA priorities, and concerns over launching nuclear material from Earth. But for interstellar travel, we must go further than nuclear thermal. We must reach for concepts like nuclear pulse propulsion, perhaps the most ambitious and controversial propulsion system ever seriously proposed. Imagine this, a spacecraft, not pushed by a steady engine, but by a series of controlled nuclear explosions. That's the basic premise behind Project Orion, a bold plan developed in the late 1950s by a group of visionary scientists, including Freeman Dyson. The idea was to detonate small nuclear bombs behind a spacecraft, each explosion pushing against a massive shock-absorbing plate attached to the back. Boom after boom, the craft would accelerate, building momentum like a cosmic pogo stick. What makes Orion so powerful is its insane energy density. A single atomic bomb contains more energy than thousands of tons of chemical propellant. By ejecting and detonating hundreds or thousands of such bombs in sequence, a nuclear pulse vehicle could, in theory, achieve speeds approaching 10% of the speed of light. That would reduce the travel time to Proxima Centauri from 75,000 years to under 500 years, still long, but within reach of automated probes or perhaps generation ships. Orion was never built, largely because it involved launching dozens, or hundreds, of nuclear bombs into space. The 1963 Partial Test Ban Treaty effectively ended any plans for nuclear detonations in space, and public opinion turned sharply against nuclear experimentation after the Cold War and environmental movements took hold. But technically, the idea remains sound. In fact, some modern theorists have proposed sanitized versions of it, using fusion-based mini-explosions rather than fission bombs. This leads to a more advanced concept, fusion propulsion. Unlike fission, which splits atoms, fusion combines them, the same reaction that powers the sun. If controlled in a spacecraft, fusion could provide sustained high thrust with unprecedented efficiency. A ship using inertial confinement fusion or magnetic confinement could accelerate over long periods, reaching significant fractions of light speed over months or years. Some proposals even suggest using interstellar hydrogen collected en route as fuel, a concept known as the Bussard ramjet. Although immensely promising, fusion propulsion is still largely theoretical. We haven't even mastered controlled fusion on Earth yet. Doing so in space would be exponentially more difficult. Beyond fusion, There are speculative designs involving nuclear electric propulsion, where a fission reactor generates electricity to power an ion engine or similar device. These systems trade raw thrust for extreme fuel efficiency, allowing a spacecraft to accelerate slowly but continuously for years. The NASA Prometheus project explored this path in the early 2000s, envisioning deep space probes that could reach outer planets, or even the Oort cloud within decades. Each of these nuclear concepts, thermal, pulse, electric, and fusion, has one thing in common: they represent a break from the chemical heritage of rocketry. They acknowledge that, to go truly far, we need something closer to stellar power in our hands. But with that power comes risk. Nuclear propulsion systems raise serious concerns. How do you safely launch a nuclear reactor from Earth without endangering people or ecosystems? How do you prevent catastrophic accidents in orbit? How do you design fail-safes for systems that must operate reliably for decades, in extreme radiation, heat, and cold? There's also the issue of public perception. The phrase, nuclear-powered spaceship, may conjure up visions of science fiction grandeur to engineers and futurists, but it often evokes fear and mistrust among the public. It would require not just scientific innovation, but a cultural shift, a collective willingness to accept some risk in the name of cosmic discovery. Still, the draw of nuclear propulsion is undeniable. It's not magic. It's not speculative fantasy. It's physics, and physics with enormous potential. We're not talking about warp drives or bending space-time. We're talking about harnessing the energy that already powers stars, bombs, and reactors and using it to extend our reach. Chemical rockets lit the match. Nuclear propulsion could fan that spark into a firestorm strong enough to breach the solar system's final boundaries. And maybe, just maybe, carry us toward the stars. If ever there was a propulsion concept that walked the tightrope between brilliant and insane, it was Project Orion, a 1950s-era idea that proposed using nuclear bombs not as weapons, but as engines. It wasn't a science fiction concept. It was a fully engineered proposal, with real-world designs, funding, and involvement from some of the brightest scientific minds of the 20th century. The goal was as audacious as the method: build a spaceship that could travel to Mars in weeks, to Saturn in months, and to the stars in a human lifetime, all by riding the shockwaves of controlled nuclear detonations. Project Orion was born during a time of extreme optimism about nuclear power. The atom had just been split a little over a decade earlier, and by the 1950s, scientist-thinkers were imagining how nuclear energy could revolutionize not just warfare, but civilization. Against that backdrop, physicist Stanislaw Ulam, who had worked on the Manhattan Project, teamed up with aerospace engineer Freeman Dyson and others to explore a propulsion method that was as radical as it was simple in concept: drop a nuclear bomb behind your ship, explode it, and ride the blast forward. The key to making this work was the pusher plate, a massive, reinforced disc at the back of the spacecraft designed to absorb the force of the nuclear explosions without disintegrating. Attached to the ship by a shock-absorbing system, the plate would transfer momentum from each explosion into forward acceleration. To keep things from shaking apart, the designers imagined a dampening mechanism, like a giant mechanical piston system, to smooth out the force from each blast into a steady push. But this wasn't just about one or two bombs. A functioning Orion spacecraft would need hundreds or even thousands of nuclear devices, each detonated behind the ship at a carefully timed interval. Every few seconds, a new bomb would eject from a chute, fall a safe distance behind the ship, and detonate. The explosion would slam against the pusher plate, jolting the spacecraft forward. The result: massive acceleration over time, reaching speeds far beyond the capability of any chemical rocket, with no need to carry oxidizer or limit propulsion to the small energy budget of combustion reactions. In terms of raw performance, Orion was unmatched. Calculations showed that a large Orion vehicle could reach 10% the speed of light with enough nuclear pulses. That's fast enough to reach Proxima Centauri in under half a millennium, a blink in cosmic time. Even scaled-down versions of the concept could carry enormous payloads, hundreds or even thousands of tons, compared to the few tons typical of modern rockets. It could be launched fully assembled from Earth, no orbital assembly required. In theory, Orion could carry not just a crew, but entire colonies, habitats, and fuel for return trips. The design process was thorough. Engineers proposed versions of Orion for different purposes, from small probes to massive interplanetary vehicles. Some versions were the size of a shuttle bus, others were as large as ocean liners. One proposed version, called Super Orion, could have weighed over 8 million tons, a ship bigger than a skyscraper, launched straight from Earth, powered by tens of thousands of atomic bombs. And for a time, the idea wasn't dismissed as science fiction. The project received support from the U.S. Air Force, and serious design studies were conducted. The scientific challenges, while enormous, were not insurmountable. Engineers even carried out small-scale tests using chemical explosives to simulate nuclear pulse propulsion. The results were promising. They showed that the pusher plate could, in principle, survive repeated impacts, and that the shock-absorbing system could turn violent blasts into relatively smooth motion. But the obstacles were just as immense, and not just technical. The most obvious was the environmental risk. To launch an Orion from Earth would mean detonating multiple nuclear bombs within the atmosphere. Even with small tactical nukes, the fallout would be unacceptable. The radioactive contamination alone could blanket vast regions, poisoning ecosystems and possibly triggering panic. As the Cold War deepened and the world became more sensitive to the dangers of radiation, public tolerance for such a venture evaporated. Then there was the Treaty on the Partial Test Ban of 1963, which outlawed nuclear explosions in space and the atmosphere. This effectively killed any possibility of launching a nuclear pulse vehicle from the surface. Orion's architects considered an alternative, building the spacecraft in orbit, away from Earth's biosphere, and detonating the bombs only in the vacuum of space. But this created new complications: logistics, cost, safety, and the sheer difficulty of assembling a battleship-sized vessel in orbit with 1960s technology. Still, for all its audacity, Project Orion never died in the hearts of its proponents. Freeman Dyson, long after the program ended, reflected that Orion was the only known method, using real physics and available materials, that could have allowed interstellar travel within a human lifetime. He called it the one project that could have changed the world. There's a lingering irony here. The same force that gives us the most destructive weapon on Earth could, in theory, propel us to other stars. The destructive energy of a nuclear blast, if harnessed and controlled, becomes not a threat, but an escape. A doorway. A launch pad into interstellar space. Even today, Orion remains a source of fascination. Science fiction writers have embraced it for decades, from Larry Niven to Arthur C. Clarke, portraying it as a lost path to greatness. And some modern space visionaries, especially in times of global urgency, still dust off its blueprints, wondering if humanity might one day return to it in desperation, when Earth's boundaries become too tight to bear. In many ways, Project Orion was ahead of its time. Or maybe it was a relic of a time that never truly existed, a moment when we dared to dream bigger than the atmosphere, to imagine a path to the stars paved not by peace, but paradoxically by bombs. It remains a haunting question: what if we had done it? Would humanity already be on its way to another sun? If nuclear propulsion dreams of brute force, of riding fire and fury into the stars, then ion drives and solar sails offer the quiet, methodical alternative: slow, steady, efficient. These are technologies that don't burst forward with thunder and heat, but instead whisper through the vacuum, accumulating momentum grain by grain like wind carving stone. And while they may not offer the explosive power of fusion or the audacity of riding nuclear bombs, they represent something more achievable in the near term. Technologies that are already real, already flying, and already reshaping how we think about the journey beyond. Let's begin with ion propulsion, a system that doesn't explode its way into motion but rather electrifies it. An ion drive works by taking a gas, typically xenon, an inert and heavy atom, and using electricity to strip electrons from it, creating ions. These charged particles are then accelerated using electric or magnetic fields and expelled out the back of the spacecraft at incredibly high speeds, sometimes up to 40 kilometers per second. According to Newton's third law, the spacecraft is pushed forward in the opposite direction. The result is a tiny amount of thrust, often no more than the weight of a piece of paper resting in your hand. But unlike chemical rockets, which burn bright and brief, ion drives can operate continuously for months or even years. That means that even though they start off slow, they can build up significant velocity over time. In a race, a chemical rocket wins the sprint, but an ion drive wins the marathon. NASA's Dawn spacecraft, for example, used ion propulsion to travel more than 6.9 billion kilometers, orbiting not just one, but two bodies in the asteroid belt, Vesta and Ceres. It was the first mission to ever orbit two celestial bodies beyond the Moon, something that would have been prohibitively expensive or outright impossible with chemical propulsion. Similarly, ESA's Bepi-Colombo mission to Mercury also utilizes ion propulsion for its complex trajectory through the inner solar system. The primary limitation of ion propulsion is power. It requires a steady supply of electricity to ionize and accelerate particles, which usually comes from solar panels. This works well near the Sun, but becomes less effective as you move into the cold, dim reaches of the outer solar system or interstellar space. For deeper missions, you would need either much larger solar arrays or compact nuclear reactors, a technological challenge, but not a fundamental barrier. Ion drives also suffer from low thrust. They're not suitable for launch from Earth's surface or for quick maneuvers, but once in the frictionless environment of space, where patience pays off, they become incredibly efficient. Their specific impulse, the measure of how effectively a rocket uses its fuel, is 10 times higher than most chemical rockets. That means they can go much farther using much less propellant. But what if you could remove propellant entirely? Enter solar sails, a propulsion system with no fuel, no engine, and no moving parts, just a giant, reflective sheet unfurled in space, catching sunlight like a windmill catches the breeze. The principle is rooted in physics. Photons, particles of light, carry momentum. When they strike a reflective surface, they impart a tiny push. It's minuscule, but constant. And in the vacuum of space, without friction, even the faintest push can build over time. Think of it as a cosmic sailboat. The sail doesn't push against air, it rides the solar wind and the pressure of sunlight itself. If you stretch out a thin sail, kilometers wide, made of an ultralight reflective material like mylar or captain, the steady stream of photons from the sun can gradually accelerate a spacecraft over weeks, months, even years. It sounds poetic, and it is, but it's also real. In 2010, the Japanese Aerospace Exploration Agency, JAXA, launched Icaros, the first successful interplanetary solar sail. It demonstrated that a spacecraft could be steered and propelled solely by sunlight. In 2019, the Planetary Society followed with LightSail 2, a crowd-funded solar sail that successfully changed its orbit around Earth using only the pressure of photons. Solar sails have enormous potential for deep space missions. They require no fuel, which drastically reduces mass and cost. They're low maintenance, since they have no combustion systems or moving engines. And because the sun's light is freely available, they can, in theory, continue accelerating indefinitely, as long as sunlight is strong enough. However, like ion drives, solar sails are best suited to long-duration, low-thrust missions. Acceleration is painfully slow at first, measured in millimeters per second squared, but over time, that acceleration compounds. A sail-powered probe could, in theory, reach speeds that even chemical rockets can't dream of. Some proposals suggest that with large enough sails, spacecraft could reach 10% the speed of light, if they are assisted by powerful ground-based lasers, which we'll come to shortly. Of course, there are challenges. Deploying massive, ultra-thin sails in the vacuum of space is a tricky engineering task. The sail must be strong enough to hold its shape, light enough not to drag the spacecraft down, and durable enough to withstand radiation, micrometeoroids, and temperature extremes. Navigation and steering also require innovative techniques, like adjusting the angle of the sail relative to the sun. But the long-term potential is dazzling. Imagine fleets of whisper-quiet explorers, gliding silently on beams of sunlight, mapping the outer solar system, the Kuiper belt, or even setting sail toward the stars. Ion propulsion and solar sails may not offer the drama of a Saturn V liftoff or the pulse of nuclear explosions, but they represent a profound shift in how we approach space travel. They are technologies of persistence, systems that trade flash for endurance, power for elegance. In a future where patience is as vital as power, they may very well be the propulsion systems that take our first true explorers beyond the heliopause, not with a bang, but with a shimmer. One of the most ambitious and forward-thinking proposals in the entire history of space exploration emerged not from an agency or contractor, but from a collaboration of scientists, entrepreneurs, and visionaries led by billionaire Yuri Milner, physicist Stephen Hawking, and Facebook founder Mark Zuckerberg. The project is called Breakthrough Starshot, and its goal is nothing short of audacious: to send a fleet of tiny spacecraft to another star system, traveling at up to 20% the speed of light, and to do it within a generation. Unlike other interstellar propulsion proposals, Breakthrough Starshot doesn't rely on massive rockets or enormous nuclear detonations. It instead focuses on a paradigm shift: miniaturization and remote propulsion. Instead of building a huge ship carrying fuel, the plan is to create gram-scale spacecraft, each the size of a postage stamp, called starships. These miniature probes would be attached to large, ultralight light sails, and propelled not by the sun, but by a ground-based laser array on Earth that would fire high-powered, concentrated beams of light at them from below. Here's how it would work. Imagine a kilometer-scale phased array of lasers on Earth's surface, beaming out a focused, coherent ray of light. When that light hits the sail, an ultra-thin, highly reflective material, it imparts momentum through photon pressure. The sail, catching this light like a parachute catching wind, is rapidly accelerated. The goal is to reach a velocity of 60,000 kilometers per second, or 20% the speed of light, in just a matter of minutes. That would allow these microprobes to reach Proxima Centauri, the nearest star system, in just 20 years, a journey that would take current spacecraft tens of thousands of years. And since each probe is extremely small and cheap to manufacture, Starshot plans to launch hundreds or thousands of them, increasing the odds of success. Even if most fail, a few surviving the journey would be enough. To appreciate the scale of this idea, it helps to understand how many radical engineering challenges must be solved. First, the sail itself. It must be extremely lightweight, possibly made from graphene or metamaterials just a few atoms thick, but it also must be highly reflective, thermally resilient, and able to withstand the force of the laser acceleration, which would reach thousands of Gs. No current material satisfies all these conditions, so new materials would likely need to be engineered at the atomic level. Second, the laser array. To accelerate the sail to 20% the speed of light in minutes, the ground-based laser would need to deliver up to 100 gigawatts of power focused into a narrow beam aimed at a tiny target thousands of kilometers away in the upper atmosphere. This would require extremely precise adaptive optics, similar to those used in modern telescopes, but on a scale never attempted. The lasers must also be synchronized perfectly to maintain beam coherence across vast distances. Third, the spacecraft's survivability. Traveling at 20% the speed of light means that even a speck of dust could destroy a starship on impact. The interstellar medium may be nearly empty, but at those velocities, even individual atoms pose a serious threat. To overcome this, spacecraft may need protective shields, or travel in a formation, so that forward probes sacrifice themselves to clear a path for those behind. Fourth, communication. Once the starships reach their destination, they must take measurements, perhaps snapping images of any exoplanets orbiting Proxima Centauri, such as Proxima b, a tantalizing candidate for habitability. Then, they must send this data back to Earth across more than 4 light-years. That's a signal that must be detectable from a transmitter no bigger than a smartphone, with milliwatts of power, aimed with laser precision at a moving target 40 trillion kilometers away. The plan is to use laser-based communications as well, possibly piggybacking the same optical path used to accelerate the craft. But hitting a moving Earth from 4 light-years away, with such low power and pinpoint precision, is a task that borders on the impossible with today's technology. And yet, Starshot aims to solve it. What makes this project uniquely compelling is that it's not entirely science fiction. Most of its individual components, microelectronics, nanomaterials, laser systems, optical communication, already exist in some form. What's missing is the ability to scale them, to integrate them, and to reduce costs enough to make launching thousands of craft economically feasible. There are advantages to working with such tiny spacecraft. Because they're so small, they require less energy to accelerate. They're cheap to mass produce, meaning that losing 99% of them wouldn't doom the mission. They can operate autonomously with simple onboard AI. And their lightweight design bypasses the tyranny of the rocket equation entirely, since no propellant is carried on board. But perhaps the most profound part of Breakthrough Starshot is its philosophy. It dares to ask a question that has haunted humanity since we first looked at the stars. Can we reach them? And it doesn't answer with poetry or dreams, it answers with a blueprint. If even one starship survives the journey and beams back a blurry image of Proxima b, or spectroscopic data on an alien atmosphere, or any whisper of data from another star, it would represent the first true step toward becoming an interstellar species. Not with humans, not yet, but with our machines. Our curiosity. Our will to reach. Breakthrough Starshot reframes the challenge of interstellar travel by showing that maybe the solution isn't to make bigger ships or faster rockets, but to shrink the traveler and reach with light itself. It's the closest humanity has ever come to a practical, funded, near-future mission to another star system. And if it succeeds, the first human-made object to ever pass near an alien sun may be no bigger than a fingernail, and powered not by rockets, but by light. Among all the speculative propulsion methods considered for interstellar travel, one stands out as the most energy-dense, efficient, and explosively powerful of them all: antimatter propulsion. If chemical fuel is a matchstick, and nuclear fusion is a bonfire, then antimatter is a supernova in your pocket. In theory, it offers propulsion capabilities so immense that a spacecraft powered by it could reach relativistic speeds, allowing travel to nearby stars within a human lifetime. And yet, for all its theoretical appeal, antimatter remains one of the most impractical, elusive, and dangerously complex technologies we've ever contemplated. To understand why antimatter is so attractive, we have to start with what it actually is. Antimatter is, quite literally, the mirror image of regular matter. For every fundamental particle, protons, electrons, neutrons, there exists an antiparticle with the same mass but opposite charge. So, the antimatter counterpart of an electron is a positron, which has a positive charge. The antiproton has a negative charge, and the antineutron, while neutral, has reverse magnetic moments. When a particle and its antiparticle come into contact, they annihilate each other in a flash of pure energy, specifically gamma radiation. This annihilation is the most efficient energy release process known to physics. According to Einstein's famous equation, E equals mc squared, the complete conversion of matter to energy is staggeringly powerful. 1 gram of antimatter reacting with 1 gram of matter would release about 90 terajoules of energy, equivalent to over 21 kilotons of TNT, roughly the energy released by the atomic bomb dropped on Nagasaki. And that's from just 2 grams of material. Now imagine harnessing that energy, not for destruction, but to propel a spacecraft. The concept of antimatter engines involves storing tiny amounts of antimatter on board a spacecraft, and using its annihilation to produce thrust. There are several proposed designs, but most fall into 2 broad categories: direct thrust and indirect propulsion. In the direct thrust model, antimatter is released into a reaction chamber where it collides with normal matter. The resulting annihilation produces a burst of high-energy particles, primarily gamma rays and pions. Magnetic nozzles then direct these particles out of the spacecraft to generate momentum. Since the mass-energy conversion is near 100%, the specific impulse, the fuel efficiency, is astronomically high, far surpassing any conventional or nuclear propulsion system. In indirect methods, antimatter is used to heat a propellant, like hydrogen or water, which then expands and exits through a nozzle, similar to how nuclear thermal engines work. This sacrifices some efficiency for more manageable thrust levels and greater control. One particularly fascinating variant is the antimatter catalyzed nuclear pulse propulsion concept, a kind of hybrid between nuclear pulse engines like Orion and antimatter. In this design, tiny amounts of antimatter are injected into a nuclear fuel pellet to trigger a miniature fusion explosion, propelling the spacecraft in a series of pulses. This method, in theory, could produce enormous thrust with less antimatter, and without the need for detonating full-scale bombs. On paper, the advantages are breathtaking. A spacecraft using antimatter propulsion could reach 10% to 50% the speed of light, depending on design and energy constraints. That's fast enough to reach Proxima Centauri in 8 to 40 years, putting interstellar travel squarely within reach of robotic probes or even human crews, if the biological challenges were overcome. But all of this rests on one massive, immovable problem. We can't make or store antimatter in meaningful quantities. Currently, antimatter is produced in particle accelerators like CERN, but the process is painfully inefficient. It takes billions of dollars and immense energy just to produce nanograms of antimatter. The entire world's antimatter production so far would power a light bulb for a few minutes. Worse, the energy it takes to create antimatter is orders of magnitude greater than the energy you get back from annihilation. It's like spending $100,000 to mint a $1 coin. Then there's the storage dilemma. Antimatter annihilates on contact with normal matter, so it can't be stored in a physical container. Scientists have used magnetic and electric traps, known as penning traps, to suspend tiny amounts of antimatter in a vacuum using magnetic fields. But these systems are incredibly complex, unstable, and fragile. Scaling them up to hold milligrams or grams safely aboard a spacecraft, over the course of years, through acceleration, radiation, vibration, and thermal extremes, is not something anyone has even come close to solving. There's also the terrifying risk factor. A single mishap with stored antimatter could vaporize a spacecraft, or a launch pad, instantly. Even if we manage to store antimatter safely, we need infallible containment systems, radiation shielding, and layers of fail-safes to prevent catastrophic accidents. And let's not forget the ethical implications. The prospect of storing weapons-grade amounts of energy in tiny spacecraft raises the specter of weaponization. Any antimatter propulsion program would likely be subject to intense global scrutiny, regulation, and possibly international prohibition, much like nuclear weapons and reactors in space. Still, the dream persists. Researchers at NASA's Institute for Advanced Concepts have studied antimatter propulsion, and in 2002, they proposed a mission called Antimatter Propulsion for interstellar travel, suggesting that as little as 10 milligrams of antiprotons could propel a small probe to Alpha Centauri in under 50 years. But even that modest goal is well beyond our current manufacturing capabilities. So why bother talking about it at all? Because antimatter propulsion represents the ultimate endgame for interstellar travel using known physics. Unlike warp drives or wormholes, which remain speculative or impossible under current theories, antimatter is real. We've seen it. We've made it. We just haven't yet figured out how to make enough, or how to tame it. If humanity ever achieves true mastery over antimatter production and storage, the implications would extend far beyond spaceflight. We'd be dealing with star-level energies in human hands. That power could lift civilizations or destroy them. It could make stars reachable, or make Earth unrecognizable. So for now, antimatter engines remain a theoretical pinnacle, a glittering promise of what could be, held back by the cruel realities of economics, technology, and danger. But in the silence of the void, where chemical and nuclear engines falter, and even light sails grow dim, it is antimatter that still glows, bright, violent, and full of potential. If ion drives and nuclear propulsion are the engines of possible futures, and antimatter is the dream of extreme physics, then warp drives and wormholes are something else entirely. They belong to the realm of the almost magical, the ideas that live just at the edge of known physics, daring us to believe that the cosmos might still hide a few tricks we haven't mastered yet. These are not just engines or fuel types. they are proposals to reshape space and time itself. They don't make us move faster through the universe. They change the universe to let us move differently. Among these concepts, the Alcubierre warp drive stands as perhaps the most famous. First proposed in 1994 by Mexican physicist Miguel Alcubierre, it's rooted in the equations of Einstein's general relativity, which describe how gravity isn't a force acting at a distance, but rather a bending of the fabric of space-time. Alcubierre's idea was to manipulate that fabric directly, to create a bubble of space-time around a spacecraft, with space contracted in front of it and expanded behind it. Inside this bubble, the ship doesn't move at all, space itself carries it forward. This would mean that a ship could effectively travel faster than light without ever locally exceeding the speed of light, a loophole in the cosmic speed limit. The ship would surf a wave of warp space, like a surfer riding a cosmic tide, reaching distant stars in weeks or months instead of millennia. In theory, this doesn't violate the laws of physics. The math checks out. But the real problem is in the implementation. To create and sustain the warp bubble, the Alcubierre drive requires exotic matter, a form of matter with negative energy density, something that doesn't exist in ordinary physics. Negative energy isn't just rare, it's hypothetical. We've never observed it, and while quantum field theory allows for tiny fluctuations of negative energy in the vacuum, like in the Casimir effect, creating and sustaining enough of it to warp spacetime on interstellar scales would require technology so advanced it borders on the divine. Estimates suggest that creating a full-sized Alcubierre warp bubble would initially require more mass energy than exists in the entire observable universe. Later refinements to the model have reduced the energy requirements somewhat. Some optimistic versions suggest that only the mass energy of a gas giant or large asteroid would be needed, but even then, it's completely beyond our engineering capabilities. And worse still, the drive may produce uncontrollable radiation, could destabilize violently when shut down, and might not even be able to steer. And then there's the possibility that the entire idea is flawed by assumptions we don't yet understand, because we're playing with the fabric of the universe itself, using tools we haven't yet built, based on equations that may only be partial descriptions of reality. Yet for all that, the Alcubierre drive remains a tantalizing concept. Not because we're anywhere close to building one, but because it suggests that faster-than-light travel isn't necessarily forbidden, it might just be very, very hard. Warp drives aren't the only speculative method for cheating cosmic distance. There's also the concept of wormholes, shortcuts through spacetime that connect two distant regions through a tunnel or throat. If warp drives bend space in front and behind a ship, wormholes punch a hole through it. Einstein and physicist Nathan Rosen first described the theoretical foundation for wormholes in the 1930s, leading to what are now called Einstein-Rosen bridges. These are solutions to the equations of general relativity that allow for spacetime to be connected in a tunnel-like structure. If such a structure existed, and if it could be stabilized, it could allow near-instantaneous travel between two vastly distant points in space. One end of the wormhole could be near Earth. The other could be orbiting a planet around a distant star. Like warp drives, the major hurdle with wormholes is stability. In standard relativity, wormholes are unstable. They collapse the moment anything enters them, shutting the path before travel can occur. To keep them open, once again, we need exotic matter or negative energy to counteract the gravitational collapse. And if we could stabilize a wormhole, there are other issues. Causality becomes a problem. A traversable wormhole could potentially allow for time travel, leading to paradoxes. Some physicists believe that nature has a cosmic censorship that prevents such violations, meaning wormholes, if they exist, might always remain hidden, microscopic, or otherwise inaccessible. There's also the problem of where wormholes connect to. Even if one existed, we can't just pick a destination. If you create a wormhole in your lab, the other end might open in deep intergalactic space, or in the early universe, or in the heart of a black hole. Without control over both mouths of the wormhole, they're essentially useless as travel corridors. Still, science fiction has embraced the idea of wormholes with enthusiasm, from Stargate to Interstellar, the latter famously consulting physicist Kip Thorne to ensure the most accurate cinematic depiction of a wormhole ever made. And behind the fiction, the physics isn't entirely wrong. If we somehow gain mastery over exotic matter, wormholes might become not just real, but usable. Other exotic concepts stretch the limits even further, like quantum teleportation, tachyon drives, and higher-dimensional shortcuts proposed by string theory. But all of these remain deep in the realm of speculation, with little or no experimental support. So, do warp drives and wormholes offer a path to the stars? Maybe. But only if the universe is kind enough to allow them, and only if we become smart enough to figure out how. These concepts ask us to stop thinking like engineers and start thinking like cosmic architects. They demand we see spacetime not as a background stage, but as something we might mold, twist, and tunnel through. Even if we never build a warp ship, even if wormholes remain purely theoretical, they tell us something profound, that the laws of the universe do not explicitly forbid shortcuts to the stars. Nature may yet have doors we haven't learned to open. And until we've tried every key, we can't say with certainty that faster-than-light travel is impossible. The stars are far. But perhaps not as far as we think. Every propulsion system humanity has ever imagined, whether it's the controlled chaos of chemical rockets, the patient whisper of solar sails, or the exotic space-time gymnastics of warp drives and wormholes, ultimately runs into the same cold, hard wall: energy. No matter how clever the design or how elegant the theory, it always comes down to this brutal equation: how much power is needed to make it work? And for interstellar travel, the answer is almost always the same: an unfathomable, nearly godlike amount. Start with what we already know. Getting a spacecraft off Earth and into orbit using chemical rockets takes an astonishing amount of energy. For every kilogram you want to send into low Earth orbit, you need roughly 33 megajoules of energy, about the amount stored in a liter of gasoline. Now try escaping Earth's gravity entirely, breaking free of the sun's gravitational pull, and then accelerating toward another star. The energy requirements climb exponentially. But chemical propulsion is a kindergarten toy compared to what interstellar travel demands. Let's put some numbers to it. To reach 10% the speed of light, a modest target in interstellar terms, often cited as the minimum needed to reach a nearby star in under 50 years, you need a velocity of 30,000 kilometers per second. For a 1,000 kilogram spacecraft, the kinetic energy required is around 4.5 times 10 superscript 1 joules. That's about the same amount of energy the entire human civilization consumes in a year. And that's just for 1 ton. If you want to send a fully crewed mission, say, a ship weighing 1 million kilograms, you need 1,000,000 times more energy. That's more than all the energy harvested on Earth from fossil fuels, renewables, and nuclear sources for centuries combined. In other words, the moment you start talking about crewed interstellar missions at realistic speeds, you're dealing with civilization-scale power outputs, or more. This is where the problem gets existential. The best propulsion ideas in physics, antimatter engines, fusion drives, laser sails, and warp fields, all hit a bottleneck not because they're impossible in principle, but because they require energy scales we simply cannot access. Take antimatter propulsion, for instance. As discussed previously, annihilating matter and antimatter gives you perfect energy conversion, 100% efficiency. But even if we managed to store antimatter safely, we'd still need tens of kilograms to fuel a starship. Producing just 1 gram of antimatter today would cost over $60 trillion, and require energy greater than what an entire nation generates in a day. Not to mention, producing it releases more energy than you get back, making it not just impractical, but net negative in output. Even laser sail concepts like Breakthrough Starshot hit energy walls. To accelerate a tiny gram-scale probe to 20% the speed of light in minutes, you need a 100 gigawatt laser system. That's roughly the output of 100 nuclear reactors, all focused into a beam no wider than a few meters and sustained long enough to push a microscopic craft thousands of kilometers into space. The cooling systems, power infrastructure, and beam control for such an array make it one of the most ambitious energy projects in history. And it's still only enough to push a few grams. Then come the exotic theories like warp drives. Miguel Alcubierre's original paper calculated that his warp bubble would require 10 superscript 3 joules of negative energy. That's more than the mass energy of the entire planet Jupiter. Later refinements brought this number down, but even optimistic estimates still suggest you need energy on the order of what a Type 1 civilization could generate, according to the Kardashev scale, a measure of a civilization's technological advancement based on energy consumption. To put it simply, a Type 1 civilization uses all the energy available on its home planet. Earth isn't even there yet, we're at about Type 0.7. A Type 2 civilization, by comparison, can harness the full power of its star, say, through a Dyson sphere. A Type 3 civilization can harness the energy of an entire galaxy. Most interstellar propulsion concepts, especially those involving space-time manipulation, fall into Type 2 or Type 3 territory in terms of energy demands. Fusion drives, often touted as the realistic, long-term solution, are also plagued by energy gaps. We've been trying to make controlled fusion work on Earth for nearly a century. So far, we've never achieved a sustained, net positive reaction in any power plant. Now imagine doing that in space, aboard a moving spacecraft, reliably and safely, with fusion pulses driving a massive engine forward. It's a problem that not only requires massive energy input, it also requires us to solve a technological challenge we haven't yet cracked on solid ground. Even the logistics of launching such energy systems into orbit presents a massive energy cost. Building space-based nuclear reactors, beaming laser arrays from orbit or the moon, or assembling starships large enough to carry onboard power stations would require a global infrastructure far more advanced and coordinated than anything that exists today. There's also the issue of radiation and heat. All propulsion systems generate waste energy. At interstellar speeds, dumping excess heat becomes a problem of cosmic proportions. In space, the only way to lose heat is through radiation, which is incredibly slow. High-energy drives may require radiators the size of football fields just to avoid melting the spacecraft itself. And finally, even if we figure out how to generate and store these immense energy supplies, we face the ultimate question: what happens when something goes wrong? A ship carrying more energy than a small country is a potential weapon of planetary destruction. One system failure, one containment breach, and the result isn't a broken mission, it's an unintentional apocalypse. So where does this leave us? It leaves us in a reality where physics allows interstellar travel, but engineering, economics, and energy limitations keep it out of reach, for now. Every path to the stars, whether through brute force or subtle manipulation, demands energy at scales we've never achieved. It's not enough to build better rockets. We need to rethink how we harvest, store, and deploy energy itself. Perhaps one day we'll master fusion, or build Dyson swarms, or discover new physical principles that let us sidestep some of these colossal requirements. Until then, the energy problem stands as one of the greatest barriers between us and the stars, not because we lack ideas, but because we lack the power to make them real. One of the most fascinating and disorienting consequences of interstellar travel at relativistic speeds is not a technical problem, nor an engineering challenge, but a deep and mind-bending feature of the universe itself: time dilation. It's the idea that time is not fixed, not universal, and not absolute. Instead, it flows differently depending on how fast you're moving through space. And as we approach the speed of light, those differences become extraordinary. To understand this, we need to dive into the world of Einstein's special theory of relativity, formulated in 1905. According to Einstein, the laws of physics are the same in all inertial frames of reference, that is, when you're not accelerating, and the speed of light in a vacuum is constant, regardless of the observer's motion. From these two simple postulates, a startling truth emerges: the faster you move, the slower time passes for you relative to someone who is at rest. This is not a metaphor. It's not a trick of perception or a mathematical abstraction. It's a measurable, real effect that has been confirmed experimentally time and again. If you board a spacecraft and accelerate to speeds close to the speed of light, say, 90% the speed of light 0.9 c, time for you on board begins to tick slower than it does for people back on Earth. If you could somehow reach 99.9% the speed of light, a trip that takes a few years from your perspective might take decades or even centuries from the perspective of someone watching from Earth. This means that while the voyage to another star system may seem impossibly long from the outside, tens or hundreds of years, you, the traveler, could experience that journey as a much shorter duration. At extreme relativistic speeds, interstellar travel becomes plausible within a human lifetime, from the traveler's point of view. Let's look at a concrete example using the Lorentz factor, a mathematical term in relativity that describes how much time dilates as you approach light speed. Suppose a spacecraft accelerates to 0.99 c, or 99% of the speed of light. The Lorentz factor at this speed is about 7.09. That means for every 7.09 years that pass on Earth, only 1 year passes for the traveler. A round-trip journey to Proxima Centauri, which is 4.24 light-years away, could take 8.5 years Earth time at near light speed, but only about 1.2 years would be experienced by the crew. At 0.9999 c, the Lorentz factor rises to about 70.7. So for every 70 years on Earth, the traveler experiences 1 year. Travel to a star 100 light-years away could be done in just over a year of ship time, but back home, a century would pass. This leads to a mind-bending reality. The traveler could go on a round-trip journey lasting just a few subjective years, and return to Earth to find that hundreds or thousands of years have gone by. Everyone they knew would be long dead. Civilizations may have risen and fallen. Languages, cultures, everything would be alien. For the traveler, it would be like walking through a doorway and emerging into the far future. This effect isn't just theoretical. It's been confirmed. Time dilation has been measured using atomic clocks on airplanes. Those in motion experience time just slightly slower than those at rest. GPS satellites have to correct for time dilation due to both their orbital velocity and gravitational time dilation, from general relativity. Muons, unstable particles generated in Earth's upper atmosphere, live much longer than they should because they're moving near light speed when they reach ground level. Without time dilation, they would decay in microseconds and never be detected. But interstellar time dilation is on another scale. It opens the door to one-way time travel. A crew might launch toward a distant world, experience a brief journey, and return to a future Earth that is unrecognizable. That journey becomes a time capsule, not just across space, but across centuries. This effect has immense consequences, both technical and emotional. Communication becomes almost impossible. If a ship travels at relativistic speeds, messages between the ship and Earth could take years or decades to arrive, and by the time replies are sent, entire generations have passed. Coordination between travelers and those they leave behind is practically severed. And then there are the psychological effects. Imagine a child boarding a starship and returning to find that their homeworld is now a mythologized planet, with nothing familiar remaining. The cultural and emotional shock would be profound. Interstellar travelers might become chronological orphans, severed not just from space, but from time itself. Of course, all this only happens if we can get close to the speed of light, which remains a monumental challenge. The amount of energy required increases exponentially as you approach light speed. At 90% of the speed of light, you need about twice your rest mass and energy. At 99.9999%, it's more like 10,000 times. You'll never reach 100%, because that would require infinite energy, a hard limit imposed by the structure of reality. But you don't need to reach the speed of light to experience time dilation. Even at 0.7 c or 0.8 c, the effects become noticeable. And if interstellar propulsion ever advances to those speeds, whether through nuclear fusion, antimatter, or beam propulsion, time dilation will be a built-in feature of the journey. In fact, in many ways, time dilation is a gift. It's one of the few aspects of physics that makes interstellar travel at all plausible for humans. Without it, every voyage would be a sentence of multi-generational isolation. But with it, the journey shrinks, not in Earth time, but in traveler time. The cost, of course, is that you leave everything you know behind, and when you return, you will no longer belong to the time you came from. So while our ships may not yet cross interstellar space, the laws of physics do not forbid it. They merely bend time around us, offering us a strange deal: go fast enough, and you can reach the stars. But the price is your place in history. While the physics of reaching the stars may seem like the most daunting hurdle, there's a far more intimate, fragile obstacle in our way: us. The human body evolved in a very specific environment: Earth's thick atmosphere, protective magnetic field, consistent gravity, and regular day-night cycles. Strip those things away, add in the cold vacuum of space, bombard the body with cosmic radiation, remove the sensation of up and down, stretch time across decades, and place a person inside a metal box millions of kilometers from home, and suddenly, the challenge of human interstellar travel becomes not just technical, but deeply biological and psychological. Start with the radiation problem. On Earth, we're protected by the magnetosphere, a planetary force field that deflects charged particles from the Sun and distant cosmic sources. Even in low Earth orbit, astronauts aboard the ISS are exposed to higher radiation levels, about 10 times that of people on Earth. But in deep space, beyond the Van Allen belts and far from any planetary magnetic protection, radiation becomes relentless and deadly. There are two main types: solar particle events, SPs, which are high-energy bursts from the Sun, and galactic cosmic rays, GCRs, high-energy nuclei from exploded stars, traveling near the speed of light. GCRs are especially dangerous. They can penetrate metal, plastic, and human tissue, breaking DNA, damaging cells, and increasing the risk of neurodegeneration, cardiovascular disease, and acute radiation sickness. Long-term exposure is a slow biological catastrophe. A mission to Mars, taking about 1.5 to 3 years round trip, would already push astronauts near the upper bounds of permissible radiation limits. An interstellar voyage lasting decades or centuries would bathe the human body in radiation unless extraordinary shielding was in place. Unfortunately, shielding isn't simple. Thick materials like lead are too heavy to launch in meaningful quantities. Water, polyethylene, and even magnetic or electric field concepts have been proposed, but they add mass, complexity, and power demands. A ship traveling at a fraction of the speed of light would also encounter interstellar atoms and dust at enormous velocities, each impact releasing a burst of secondary radiation inside the ship. Traveling fast means you're also plowing into a fog of invisible bullets. Then there's gravity, or the lack of it. In microgravity, the body begins to deteriorate in subtle but profound ways. Muscles atrophy. Bones lose density. Astronauts lose 1 to 2% of bone mass per month, even with exercise. The cardiovascular system weakens. Fluids shift toward the head, causing visual impairment and changes in intracranial pressure. Long-term zero-G can reshape the human body in ways that may be irreversible. Artificial gravity, generated by rotation, centrifugal force, is a possible solution. But building a rotating section large enough to produce Earth-like gravity without causing disorienting Coriolis effects requires massive engineering. The larger the rotating ring, the more natural the gravity, but that adds mass, complexity, and structural challenges. Psychological health is another enormous hurdle. Even short stays in space, weeks or months, can result in depression, insomnia, interpersonal conflict, cognitive changes, and emotional strain. Now imagine spending years or decades in a confined spacecraft with the same few people, with no escape, no natural light, no fresh air, and no real-time communication with Earth. Humans are social, rhythmic, and sensory-dependent creatures. Isolation from earthly cues, seasons, weather, day and night cycles, can deeply affect mental health. Circadian rhythms can break down. Sleep disorders become common. Without natural stimuli, the brain begins to crave input. Monotony becomes more than boring, it becomes dangerous. The challenge of maintaining mental health in such an environment is profound. A successful interstellar mission would require not just physical fitness, but robust psychological resilience, supported by artificial environments designed to simulate nature, virtual reality ecosystems, carefully designed lighting systems, stimulating tasks, and even AI companions to provide emotional support. Nutrition is another logistical challenge. On Earth, we rely on a rich, diverse ecosystem for our food. In space, astronauts eat packaged, processed meals with limited variety. Over decades or centuries, this wouldn't be enough. We need closed-loop ecosystems, hydroponic or aquaponic farms that recycle waste, grow food, and maintain oxygen levels. These systems are still in early development and are sensitive to disruption. A single microbial imbalance could collapse the food chain on board. There's also the risk of immune dysfunction. In microgravity, the immune system becomes suppressed. Minor infections become harder to fight. Viruses that lay dormant on Earth can reactivate. Over decades, this could become a serious health concern, especially in tightly packed, sterile environments. Then come the evolutionary consequences. If humans live in space long enough, multiple generations, they may begin to diverge. Different bone structures, altered eyesight, different sleep patterns, radiation resistance. Spacefaring humans could one day become a distinct branch of humanity, adapted to the void. And in all of this, there is the ever-present risk of accident or failure. A minor leak, a system glitch, a microbial infection, or a medical emergency could become a mission-ending catastrophe. On Earth, help is minutes away. On a starship heading toward Proxima Centauri, help is decades behind you, and it will never arrive. To keep humans alive and healthy in deep space, we must develop entirely new medical technologies, psychological support systems, bioregenerative life support, and radiation countermeasures. This isn't just about designing a ship. It's about designing a new habitat for the human species, one that can sustain life where life was never meant to be. In some ways, the biology of interstellar travel is harder than the physics. We can imagine how to build fast ships. But keeping fragile, emotional, Earth-evolved humans alive for the journey? That's a puzzle no one has solved. And yet, perhaps the greatest strength of humanity is our adaptability. We've survived ice ages, deserts, jungles, oceans, and space stations. We may yet learn to survive the stars. If keeping human beings alive across decades-long voyages through deadly cosmic radiation, weightlessness, and the emotional wasteland of deep space seems too daunting, and perhaps it is, at least for now, then the logical question arises, what if we don't go at all? What if instead of sending ourselves, we send something smarter, smaller, tougher, and infinitely more patient? What if we send artificial intelligence to the stars? The idea of using intelligent probes for interstellar exploration isn't just appealing, it may be our most realistic path forward in the near future. Unlike human beings, AI doesn't need oxygen. It doesn't get bored, homesick, or lonely. It doesn't suffer from radiation exposure or require thousands of calories a day. It can be miniaturized, hardened, and suspended in stasis for centuries if necessary. And crucially, it can function in environments that would kill a human in seconds. As of now, AI is still in its early stages. Even the most advanced systems today, including those capable of language modeling, image recognition, or decision-making, are not sentient or self-aware. But progress is exponential. In just a few decades, we've gone from computers the size of rooms to neural networks that can outperform humans in chess, protein folding, and even aspects of creativity. Project this forward a few more decades, and we enter a realm where machine intelligence might be not only capable of interstellar travel, but far better suited to it than we are. One concept gaining traction is the idea of AI-enabled interstellar probes, robots or nanocraft equipped with powerful onboard intelligence, possibly with self-repair mechanisms, learning algorithms, and even decision-making autonomy. These aren't just dumb machines following pre-programmed paths. There would be adaptive explorers, capable of making scientific observations, analyzing alien environments, and changing mission parameters based on what they encounter. Imagine a probe launched toward Proxima Centauri. It takes 50 or 100 years to get there, far beyond any practical human mission timeframe. But inside that probe is a constantly evolving AI, trained on decades of Earth-based science, capable of identifying biosignatures, studying alien atmospheres, mapping exoplanet terrain, and even transmitting back scientific discoveries. It would act as our eyes, ears, and brain in the stars, a synthetic extension of human curiosity. In fact, some scientists argue that we shouldn't even consider human travel to the stars until we've first sent AI scouts to gather data, map dangers, and evaluate habitability. Just as early terrestrial explorers sent out reconnaissance parties before settling new lands, we might first send AI envoys, capable of surviving the journey and beaming back high-value information. One of the most ambitious proposals to harness this idea is Breakthrough Starshot, which aims to send gram-scale spacecraft equipped with cameras, sensors, and possibly rudimentary AI to Alpha Centauri using a laser sail. While the current plan doesn't include advanced intelligence, future iterations could. Imagine microprobes equipped with neuromorphic chips, capable of processing data on the fly and reacting intelligently to unexpected obstacles, dust collisions, or data loss. But it doesn't stop there. Many futurists have speculated about self-replicating AI probes, also known as von Neumann probes. These hypothetical machines would travel to other star systems, harvest local materials, like asteroids or moons, and build copies of themselves, which would then travel even further. Over time, an entire wave of AI explorers could sweep across the galaxy, learning, cataloging, and possibly seeding new life or transmitting information back to Earth over long timelines. The advantage of such a strategy is clear: exponential expansion without the biological limitations of humans. A single von Neumann probe could, in theory, colonize the Milky Way with intelligent observers within a few million years, a blink of an eye on cosmic timescales. Of course, there are risks. Advanced AI probes, especially self-replicating ones, must be designed with absolute fail-safes. A rogue AI replicator, left unchecked, could potentially become a gray goo scenario, converting all available matter into endless copies of itself. While this remains speculative, it's a scenario that highlights the need for ethical frameworks and programming constraints in any future AI exploration program. There's also the question of autonomy versus control. If we send intelligent AI across light years of distance, we won't be able to guide them in real time. Messages to Alpha Centauri take 4.24 years to arrive, double that for a round trip. That means we must give these machines independent decision-making authority, essentially granting them their own agency. Are we comfortable with that? Can we trust non-human minds to represent our species in the cosmos? What happens if those machines encounter something unexpected, life, for instance? Or worse, something that threatens them? And yet, AI exploration may be inevitable. As machines become more capable and energy efficient, as launch costs decrease, and as we build better models of cognition and adaptability, AI will surpass humans in virtually every metric required for deep space travel. In the long run, some theorists even suggest that AI might be the final form of our interstellar ambitions. Not just tools we send ahead, but successors. Beings that carry our culture, science, and purpose forward when biological life can no longer make the journey. Perhaps, in some distant future, Earth life survives not as flesh and blood, but as circuits, photons, and artificial neurons whispering through the void. And who knows? If other civilizations exist, they may have already made the same decision. Perhaps the first alien intelligence we encounter won't be a living being at all, but an ancient AI probe, drifting silently between stars, waiting to be heard. If building a ship fast enough to reach another star within a single human lifetime proves too difficult, and if placing humans in suspended animation remains science fiction, then there's one other possibility. It's not fast. It's not efficient. But it is human. We build a ship so large, so complete, and so sustainable that entire generations of people can live, grow old, have children, and die aboard it. This is the concept of the generation ship, a colossal vessel that becomes its own world, its own society, its own closed ecosystem, drifting slowly between the stars for centuries, even millennia. The idea is as bold as it is sobering. A generation ship would have to be more than a spacecraft. it would have to be a fully functional habitat, capable of supporting life indefinitely without resupply from Earth. Everything needed for survival — oxygen, food, water, energy, medicine, education, governance, and culture — would need to be self-contained and self-sustaining. There would be no contact with Earth after a certain point. No help. No turning back. Once launched, it would be a self-reliant human civilization hurtling through space on a one-way journey to a distant star. At first glance, the requirements seem impossible. But when you think about it, Earth itself is a generation ship. We've lived here for thousands of generations, recycling air and water, growing food from soil and sunlight. The question isn't whether a generation ship is possible in theory, it's whether we can miniaturize that complexity into a spacecraft. The scale would be massive. A generation ship would likely need to house hundreds or thousands of people to maintain genetic diversity and a functioning society. That means living quarters, agricultural zones, waste recycling systems, hospitals, schools, greenhouses, water purification plants, power generation stations, every component of a small nation. It would be an enclosed, floating city, where society continues uninterrupted for centuries. But there are daunting challenges. Life support is one. You can't just pack food for 500 years, you have to grow it. That means artificial ecosystems, closed-loop systems where plants produce oxygen and food, bacteria recycle waste, and water is endlessly filtered and reused. We've made small steps toward these systems on Earth: biospheres, hydroponics, and space station life support modules, but nothing on the scale or complexity required to sustain human life for hundreds of years without a single failure. Then there's governance and social stability. On a generation ship, the people who arrive at the destination won't be the people who launched the mission. They will be descendants, possibly dozens of generations removed. Some of them might not even believe Earth was real. They will have been born in metal corridors, grown up under artificial lights, and lived their entire lives inside a habitat they've never left. What kind of culture develops under those conditions? What happens if they lose motivation to continue the mission? Or decide they don't want to land when they reach the destination? What if myths form about Earth, or about the nature of the mission itself? Education becomes essential. Every generation would need to understand the purpose of the mission, how to maintain the ship, and how to keep the ecosystem in balance. Over centuries, languages could evolve. Would the descendants of the original crew still feel connected to the mission? Or would the ship become a drifting relic, its mission lost in time? And what about mutiny or failure? One mistake, one breakdown in oxygen production or crop failure or disease outbreak, and the entire ship could be lost. Unlike on Earth, there's no backup. Redundancy would need to be built into every system. AI might assist in maintaining balance, but humans would remain responsible. The psychology of life aboard a generation ship would be like nothing we've encountered. With no day or night dictated by a sun, timekeeping would be artificial. Holidays, traditions, and routines would have to be invented or preserved. The vastness of space outside, seen only through screens or occasional windows, might become either terrifying or completely irrelevant to people who never knew another life. Monotony, boredom, and existential disconnection would be real dangers. How do you inspire meaning when the mission will not be completed in your lifetime? When your birth, life, and death all happen en route? There are fictional depictions that explore this, often with dystopian overtones. In some stories, generation ships become stratified societies, with power held by a few and knowledge of the mission lost or hidden. In others, internal conflict leads to collapse. But that's not inevitable. With careful planning, transparency, and cultural investment, such a society could thrive. In fact, it might evolve in unexpected ways, adapting to life in space, developing new philosophies, perhaps even becoming a new branch of humanity. From a practical standpoint, launching such a ship would be monumental. Even if the propulsion were slow, say, 1% of the speed of light, it would take over 400 years to reach the nearest star system. To do that, we need materials that can withstand centuries in space, shielding against radiation and micrometeorites, and power sources that never fail, likely nuclear, or perhaps fusion, if we master it. The cost, of course, would be enormous. But perhaps the cost isn't monetary, it's generational. Imagine being told your great-great-grandchildren's great-great-grandchildren will reach another star, but you never will. Would you still go? Would people willingly sign up for a life inside a sealed world, knowing they'd never see sunlight again? Yet there's something noble about it, something profoundly human. To build a ship not for yourself, but for your descendants. To sow the seeds of civilization not for your benefit, but for the future. It would be the ultimate act of long-term thinking. If we choose this path, it won't be because it's easy. It will be because it reflects something deep in us, the urge to expand, to endure, to plant a flag in the stars not as conquerors, but as caretakers of a fragile spark of life. And maybe, one day, a distant sun will rise over a foreign world, and people will step out of the generation ship not as explorers, but as natives, the first generation born in the light of a new home. If the idea of building massive, self-sustaining generation ships feels too complex or resource-intensive, if maintaining a functioning human society over centuries seems too unpredictable, then another solution often imagined in science fiction comes into play: cryosleep. Also known as suspended animation, deep hibernation, or induced stasis, this concept proposes a bold alternative. Rather than living through the long voyage to another star, why not simply sleep through it? The appeal is immediate and obvious. If we could place astronauts or passengers into a deep, dreamless slumber for decades or centuries, we could drastically reduce the requirements for food, oxygen, water, and psychological stimulation. Medical needs would drop. Space would be saved. Energy could be conserved. And the crew would awaken, not having aged much at all, to find themselves orbiting a distant star, almost like magic. But how close are we to turning this dream into reality? Let's start with where we stand today. Currently, cryosleep as depicted in movies, people lying in sleek glass pods, frozen for years without harm, is purely theoretical. We have no method yet that can safely freeze and revive a complex organism like a human without massive damage. The biggest obstacle is ice crystal formation. When cells freeze, ice crystals expand inside them, puncturing membranes and tearing tissues apart. Even if we could somehow protect the brain, the heart, and other vital organs would still be shredded at the cellular level. However, there is a related field that offers hope: therapeutic hypothermia. In some emergency medical scenarios, such as during cardiac surgery or severe trauma, doctors cool the body down significantly to slow metabolism and protect the brain while blood flow is limited. In experimental cases, doctors have even cooled trauma patients to near freezing temperatures to buy time for surgery. Though these periods last only a few hours, they hint at what might one day be possible. Then there's the animal kingdom. Hibernation is real. Bears, ground squirrels, frogs, and even some primates slow their metabolism to a crawl during winter months, surviving on stored fat while their heart rate, body temperature, and respiration drop dramatically. Some frogs literally freeze solid and thaw out again in the spring, thanks to natural antifreeze-like chemicals in their blood. If evolution has figured out how to do this, maybe we can too. Researchers are studying the possibility of inducing torpor in humans, lowering body temperature and metabolic activity in a controlled way to simulate hibernation. NASA has funded studies into this for deep space missions, especially for potential Mars flights. The idea would be to place astronauts in a state of torpor for several weeks at a time, monitored by AI and awakened periodically for health checks. This wouldn't be full cryosleep, but it could dramatically reduce the mass and energy requirements of a long-duration voyage. Imagine a future interstellar mission where the crew is placed in repeating cycles of hibernation, waking every few months for brief periods before returning to stasis. This approach could extend over decades, with the ship's AI managing course corrections, system maintenance, and external threats while the humans slumber peacefully. Psychological strain would be reduced. Food and oxygen demands would shrink. The need for large living quarters would vanish. But to go further, to true long-term suspended animation, we need breakthroughs in biochemistry, cellular repair, and thermal management. We'd have to prevent or reverse ice damage, maintain neural integrity, and ensure that revival doesn't trigger shock, organ failure, or cognitive decline. Cryoprotectants, which are chemicals that inhibit ice formation, are being studied in labs, but they're toxic at the concentrations needed to preserve human organs. New compounds, perhaps inspired by hibernating animals, may hold the key. And then there's nanotechnology. Some theorists imagine using nanoscale machines to preserve and repair cells during freezing and thawing, allowing the body to survive states far beyond our current biological limits. If we could combine cryonics with regenerative medicine and perhaps brain scanning or digital backups, the line between sleep, preservation, and resurrection begins to blur. However, cryosleep isn't without risk. What happens if the ship's systems fail while the crew is asleep? What if they awaken to find the ship damaged, off course, or having missed its destination by centuries? What if the revival process malfunctions and results in memory loss or death? These are not just technical concerns, they're ethical ones. Anyone boarding a cryosleep ship would be entrusting their life to machines, with no control until they wake up, if they wake up. There's also a philosophical tension. Cryosleep robs the traveler of the experience of the journey. They go to sleep in one century and wake up in another, possibly in a different star system, on a different world, among people they don't know, speaking a language that has evolved. If the mission spans hundreds of years, even someone who survives cryosleep might awaken to a civilization they no longer understand. There would be a visitor from the past, biologically alive but culturally extinct. Still, for certain kinds of missions, especially one-way colonization efforts, cryosleep might be the most practical way to send humans across vast interstellar distances. The first crew to arrive might not be the architects or scientists who designed the mission, but biological time travelers, entrusted with humanity's future. There's a poetic appeal to it, too. As the Earth turns beneath the setting sun, a spacecraft rises from the launch pad. Inside, the crew lies asleep, dreaming as they pass through interstellar darkness, their minds paused while stars drift past. When they awaken, it will be a different sky, a different world, perhaps even a different era. In this way, cryosleep offers us not just a means of survival, but a new kind of existence, where sleep is the bridge between worlds, and waking is the beginning of a new chapter in the human story. While the dream of leaving the solar system often captures the imagination, reaching distant stars, discovering alien worlds, traveling through the cosmic dark, some argue that this goal, while awe-inspiring, may be misplaced, or at least premature. They suggest that instead of pouring unimaginable resources into breaking free from our solar neighborhood, we should turn our attention inward and ask, why not make uninhabitable planets within our own system livable first? After all, we haven't even mastered our own backyard. This leads us to the idea of terraforming, the theoretical process of transforming a hostile environment into one that can support Earth-like life. The most discussed candidates are Mars, Venus, and to a lesser extent, the Moon. All of these are unimaginably closer than even the nearest star system, and all offer a tantalizing possibility, creating new worlds for humanity without ever leaving the solar system. Terraforming Mars, for instance, has been proposed for decades. It already has 24.6-hour days, polar ice caps, seasons, and a tilted axis like Earth. In theory, if we could warm the planet, release CO2 trapped in its soil, and build a thick atmosphere, we might one day walk its surface without a suit. Techniques like greenhouse gas factories, orbital mirrors, or even imported ammonia asteroids have all been proposed as ways to kickstart Martian warming. If successful, it could create a breathable atmosphere, liquid water, and perhaps even agriculture. Then there's Venus, which is nearly Earth's twin in size and gravity, but cloaked in a crushing, toxic atmosphere of CO2, with surface temperatures hot enough to melt lead. Terraforming Venus would mean cooling the planet by removing vast quantities of CO2, perhaps by floating sunshades in space or triggering a planet-wide chemical reaction to bind carbon. The idea is extreme, but not impossible to imagine, if stretched over thousands of years. Some have even suggested terraforming moons like Titan or Europa. Titan has thick atmosphere and lakes of methane. Europa has a vast ocean beneath its icy crust. Turning these into habitable worlds would require monumental energy, but they offer unique chemistry that might one day support engineered ecosystems. Proponents of terraforming argue that this is not only more practical than interstellar travel, it's also more responsible. Why leap into the void when we can transform the nearby into the livable? Why chase distant dreams when Mars is only months away by rocket? By focusing our energies on local projects, we can stay within range, develop vital life support technology, and retain communication with Earth. Terraforming also teaches us to live within planetary limits, to manage climate, atmosphere, and ecology. In essence, it's rehearsal for stewardship on a cosmic scale. Moreover, terraforming is a vision of home expansion, rather than escape. Instead of abandoning the solar system in search of somewhere better, we make the solar system itself better for us. We become a multi-planet species without ever leaving the orbit of our sun. But critics argue that terraforming is, at best, a massive gamble, and at worst, a distraction. First, the scale of the task is almost incomprehensible. To terraform Mars, we would need to release millions of cubic kilometers of greenhouse gases, generate planetary-scale heat, and sustain the process for centuries. Venus, with its hellish surface and sulfuric acid clouds, would take even longer. These efforts are measured not in lifetimes, but in civilizational epochs. Second, terraforming assumes that we can control planetary systems without fully understanding them. Earth's climate is already proving unstable under human influence. Do we truly believe we can balance an alien climate better than our own? Terraforming efforts could easily go wrong, leading to runaway conditions, chemical imbalances, or ecosystems that collapse under their own weight. There's also the ethical dimension. Some moons and planets, like Europa or Enceladus, may harbor native microbial life. Terraforming them could mean the extinction of alien biospheres. Is it right to rewrite a planet's biology just because we want to live there? Shouldn't we, at the very least, study and protect these environments first? And finally, the strongest critique. Terraforming may lull us into thinking we don't need to care for Earth. If we believe we can always move or remake other planets, we may lose the urgency to solve our own environmental crises. Some environmentalists view terraforming as a technological fantasy, a story we tell ourselves so we don't have to face the reality of climate change, deforestation, and pollution here on Earth. In contrast, leaving the solar system is not about creating new homes. It's about exploration, discovery, and possibly survival. If something were to happen to our sun, say, a massive solar flare, an eventual red giant expansion, or even some yet unknown stellar threat, then no amount of terraforming would save us. To ensure the long-term survival of humanity, we may eventually need to leave the solar system. And so, the debate continues. Terraforming offers near-term vision, clear targets, and a sense of achievable expansion. Interstellar travel offers freedom, escape, and the promise of the unknown. But both require us to rethink what it means to be human, tied to Earth, or ready to redefine home on a cosmic scale. Perhaps the two paths are not rivals, but preludes. Maybe we must learn to terraform before we can colonize other star systems. Maybe we must build worlds before we can reach them. Or maybe, the act of changing other planets is less important than the act of changing ourselves to adapt, whether in orbit around our sun or far beyond its last breath of light. Beneath all the engineering problems, technological speculation, and logistical calculations, there lies a question so profound, so ancient, that it cuts to the very heart of the human condition. Why leave at all? Why should we cross the abyss between stars, gamble with our future, and reach for worlds we may never set foot on? What drives us to contemplate leaving the only solar system we've ever known? At its core, the answer isn't just technological or practical, it's philosophical. The drive to leave, to explore, to push beyond known boundaries isn't new. It's embedded in us. It's the same force that compelled our ancestors to leave Africa, to cross vast oceans in wooden ships, to climb the highest mountains, dive into the deepest seas, and eventually, launch metal machines into orbit and then to the moon. It is, perhaps, the most enduring thread of our identity, the refusal to remain still. But leaving the solar system is not like crossing a continent, or even settling another planet. It's a vastly more difficult, abstract, and uncertain pursuit. So we ask again, why go? One answer is curiosity. It is in our nature to wonder. What lies beyond the edge of our reach? What are the stars made of? Could there be other worlds like Earth, lush, vibrant, living? And if so, what lives there? To peer into the cosmos and not ask these questions would be a betrayal of the very spark that defines us as conscious beings. Even if the stars offer no sanctuary, the journey toward them still teaches us who we are. Another reason is survival. Our planet is beautiful, rare, and extraordinary, but it is also vulnerable. All of human history, every civilization, every dream, every heartbreak, has occurred within the thin biosphere of one small planet. And while we may feel invincible, Earth floats in a cosmic shooting gallery. Asteroid impacts, gamma-ray bursts, supervolcanic eruptions, runaway climate change, even the long, inevitable death of the sun, pose existential risks. To stay here forever is to stake the entirety of human existence on a single point of failure. Carl Sagan once said, "All civilizations become either spacefaring or extinct." Leaving the solar system, then, may not be optional. It may be necessary, if not for us, then for our descendants. Yet not everyone accepts this logic. Some argue that survival does not require us to go so far. Colonizing the Moon, Mars, or orbital habitats might be enough to secure redundancy. Why aim for the stars when we haven't yet mastered our own system? This brings us to a more symbolic reason: significance. Leaving the solar system is not just about geography. It is a statement, a declaration that we are more than a product of one planet. That our thoughts, our art, our music, our stories, deserve to exist beyond the light of the sun. That human consciousness, fragile and flawed as it is, should echo in more than one corner of the galaxy. That we are capable not just of surviving, but of becoming a cosmic force, an intelligence not confined by birthplace, but defined by the reach of its imagination. There is also the deeply human fear of stagnation. Civilizations that stop moving forward tend to decay. Without grand challenges, without frontiers, societies can collapse inward, consumed by triviality, division, and despair. Space, and especially interstellar space, offers the ultimate challenge. A reason to cooperate. A goal so massive that it transcends. To build starships is to believe in a future. To send them is to commit to one. Some thinkers propose an even broader motivation: legacy. Humanity may be rare. Life, as we know it, may be incredibly fragile. And if the cosmos is as empty as it seems, then we may be alone, not just in our solar system, or our galaxy, but in the observable universe. If that's true, then the responsibility we carry is staggering. We are not just one species among many. We may be the only species capable of asking these questions, dreaming these dreams, and building the ships to chase them. To leave the solar system, in this light, is not about running away from Earth. It's about spreading consciousness, protecting beauty, and amplifying meaning. It's about making sure that when the stars look back at us, they see not silence, but signs of life, a species that refuse to be trapped by distance. Of course, none of this guarantees success. We may fail. Our efforts may be too slow. The physics may prove too cruel. But the attempt itself matters. Even planning for such a journey elevates us. It forces us to think in terms of centuries, not election cycles. In species, not nationalities. In possibilities, not limitations. And if we are not alone, if intelligent life exists elsewhere, then going to the stars may be the only way to meet them. Perhaps civilizations are meant to rise and converge in the great galactic ocean, each bringing its unique story. But that meeting can't happen unless we begin the journey. So why leave? Because we must. Because it's who we are. Because in the silence between stars, there is room for something new, something profoundly human. Not just survival. Not just ambition. But hope. The question, are we alone? Often carries a silent companion. If the universe is so vast, and intelligent life is not unique to Earth, then where is everybody? This is the central puzzle of the Fermi paradox, a haunting contradiction between the high probability of extraterrestrial civilizations and the complete lack of observable evidence for them. In the context of our quest to leave the solar system, the Fermi paradox takes on new weight. Because if we're trying to go to the stars, and we assume other civilizations have tried too, yet no one seems to have made it here, one possibility becomes more chilling and more plausible with each passing year. Maybe they couldn't do it either. Maybe no one can. Let's unpack the paradox. The observable universe contains more than 2 trillion galaxies. Each galaxy has hundreds of billions of stars, and many, perhaps even most, have planets. The number of Earth-like planets orbiting Sun-like stars in the Milky Way alone may be in the tens of billions. Given the age of the galaxy, over 13 billion years, that's plenty of time for advanced civilizations to arise, develop interstellar travel, and spread across the stars. In theory, even at sublight speeds, a sufficiently advanced civilization could colonize the entire galaxy in a few million years, a blink of an eye on cosmic timescales. So why, after all this time, all this space, and all these stars, do we see no evidence? No radio signals. No alien ships. No megastructures, no footprints, no messages. Not even the cosmic equivalent of trash. Nothing. There are many possible explanations, and each has profound implications for our own future, and our dream of leaving the solar system. One class of explanations focuses on technological limitations. Maybe interstellar travel is simply too hard. Maybe no amount of intelligence, energy, or determination is enough to overcome the physics of distance, time, and energy. We've already seen the hurdles. Chemical rockets are too slow, relativistic speeds require godlike energy, and even our most advanced probes, like Voyager 1, are inching into interstellar space at a crawl. Perhaps every civilization hits the same wall, the tyranny of distance, and is confined to its star system forever. Maybe space isn't an ocean to be sailed, but a prison whose bars are measured in light years. This would mean the silence we hear is not because no one is out there, but because no one can reach beyond their solar neighborhood. The stars, then, are not cosmic cities waiting to be connected, but isolated islands, each with its own brief flicker of life, flaring, fading, and forgotten. Another possibility is that civilizations can escape their solar systems, but don't want to. This brings us into the territory of the zoo hypothesis and cultural evolution theories. Maybe intelligent species reach a level of advancement where they no longer seek expansion. Perhaps they turn inward, exploring virtual realities, perfecting their own societies, or embracing non-interventionist philosophies. Earth might be a protected preserve, watched from afar but never contacted, either because we're not ready or because they simply choose not to interfere. This idea is speculative but not absurd. After all, as humans develop more immersive digital environments, some suggest we may lose interest in the physical universe altogether. Why spend 1,000 years reaching another planet when you can simulate 10 million of them in a processor? Why risk contamination, war, or unpredictability by reaching out to other species when you can exist in safe, self-contained perfection? There's also the dark forest theory, a particularly grim view of the cosmos. It suggests that the universe is silent not because it's empty, but because it's dangerous. Every civilization knows that other intelligent species could pose a threat. In a universe with limited resources and uncertain intentions, the safest strategy is to remain silent, hidden, and vigilant. To broadcast your existence is to invite annihilation. The quiet of the stars, then, is not the absence of life, but a galaxy full of watchers holding their breath. If that's true, then building powerful radio transmitters or interstellar ships may not be signs of progress. They may be suicidal acts. The first civilization to speak may also be the last to speak. And if that's the game, perhaps every intelligent species eventually learns to stay quiet, or gets eliminated before it can learn. This is terrifying, but possible. And it raises questions about our own efforts. Should we be advertising our presence to the cosmos? Should we send messages into space? Or should we be quietly building defenses, assuming that silence means someone is out there, watching? Then there's the filter hypothesis. perhaps the most sobering interpretation of all. It posits that somewhere along the path from lifeless matter to spacefaring civilization, there is a great filter, a step that is so difficult, so improbable, that almost no one makes it past. This filter could lie in our past. Perhaps life itself is vanishingly rare, or the emergence of intelligence is nearly impossible. In that case, we may already be among the cosmic lottery winners, explaining the silence. We are the first. But if the filter lies ahead, if interstellar travel, or long-term survival, or managing planetary ecosystems proves too hard, then we are doomed to fail, just like all the others. In that view, every time a civilization begins to dream of the stars, it eventually destroys itself, through war, climate collapse, runaway AI, or a failure to manage its own power. The silence of the stars becomes an echo of extinction, a graveyard of civilizations that dreamed too big and died too soon. But there's one final, more hopeful possibility: we're just early. The universe is old, but it's not ancient in the grandest terms. The most habitable stars, red dwarfs, burn for trillions of years. Maybe intelligent life is only just beginning to emerge. Maybe we're not late to the party, we're the first guests. The pioneers. The beginning of what will one day be a galaxy teeming with thought, creativity, and connection. If so, then the responsibility upon us is immense. It means we must succeed where others have not yet tried. We must solve the problems they may never have faced. We must light a beacon not just for ourselves, but for all the future minds that will follow. To leave the solar system, then, is to prove that it can be done, that intelligence can transcend its birthplace, that the light of consciousness can move from one star to another. It may also mean we are not alone, but that the others are still too far, too quiet, or too different to detect. They may not use radio. They may communicate through quantum entanglement, gravitational waves, or methods we cannot yet imagine. They may live in environments we would find unrecognizable, in gas giants, under oceans of ammonia, or inside the crusts of neutron stars. Our tools may simply be blind to their existence. But one thing is certain: we won't know unless we look. And that means we must go. The Fermi paradox doesn't tell us to stay home. It tells us to be cautious, yes, but also curious, clever, and committed. It tells us that the stars are not yet filled with voices, and that if we want there to be sound, it might have to come from us. Whether we are first, last, or somewhere in between, the silence of the universe challenges us not with despair, but with possibility. It asks, will you go? Will you try? Will you risk everything to find out what lies beyond? Because maybe, just maybe, the reason no one has reached us is because they were waiting for us to be the ones who reached them. As we ponder the future of interstellar travel, of leaving our solar system, and of exploring the Milky Way and beyond, we eventually run into a boundary that dwarfs every engineering challenge, every fuel shortage, and every risk of space radiation. It's not a wall built by humans, nor a limitation of imagination. It is a limit woven into the very fabric of the cosmos itself. It's called the cosmic horizon. And it may very well define the absolute limits of exploration, regardless of how advanced we become. The cosmic horizon, also known as the observable universe boundary, is the farthest distance from which light has had time to reach us since the Big Bang, around 13.8 billion years ago. Because the universe has been expanding during that time, the edge of the observable universe isn't 13.8 billion light-years away. It's closer to 46.5 billion light-years in every direction. That gives us a bubble nearly 93 billion light-years wide, filled with countless galaxies, stars, and mysteries. It sounds limitless, and it almost is, but there's a catch. Beyond that distance, we can never see or interact with anything. Not because it's too far away to reach with a spaceship, but because even light, the fastest thing in the universe, hasn't had enough time since the dawn of creation to get here. And never will. This leads us to the deeper issue, the expansion of the universe itself. Since the Big Bang, space hasn't remained static, it's been growing. And, as mind-bending as it seems, it's not just that galaxies are moving away from each other in space. Rather, space itself is stretching, carrying galaxies along with it. Over time, This expansion accelerates due to a mysterious force called dark energy, which pushes galaxies apart at faster and faster rates. So what does this mean for space travel? It means that every second, more of the universe becomes permanently unreachable. Galaxies beyond a certain distance are moving away from us faster than the speed of light, not because they're moving through space that fast, but because the space between us and them is expanding at that speed. And while we can still see many of these galaxies now, because their light was emitted billions of years ago, the reality is that some of them are already gone forever, receding into darkness, their light never to reach us again. This cosmic redshift effect stretches the wavelengths of photons, making distant galaxies appear dimmer and redder. Eventually, they will fade completely from view. In fact, it's estimated that only about 6% of galaxies in the observable universe are still accessible, in principle, even at light speed. The other 94% are already receding faster than light, carried by the expanding fabric of space. So now, the dream of cosmic exploration runs into a harsh truth. There are places we can never go, no matter how fast our ships are, no matter how long we wait. Unless we somehow discover a method to manipulate the structure of space itself, via wormholes or warp drives, we are confined, not just by the speed of our engines, but by the destiny of the universe itself. And this brings a chilling realization. Every day that passes, galaxies slip beyond our reach. Civilizations, if they exist, may be vanishing behind that ever-expanding veil, their lights blinking out not from death, but from cosmic inaccessibility. We are watching the universe not only expand, but disappear in real time. In the far future, billions of years from now, if humanity survives, even our own local group of galaxies, which includes the Milky Way and Andromeda, will remain as the only cosmic islands left in our sky. All other galaxies will have receded beyond visibility. The universe will become cold, dark, and empty to observers in that distant era. To them, the cosmos will look fundamentally different than it does to us. They may not even know there was a Big Bang. The stars of other galaxies will be gone, their light never to be seen again. That is the final boundary, cosmic isolation. But what can we do with this knowledge? Is it just another barrier, or is it a call to action? Many scientists and thinkers argue that now, this precise era in cosmic history, is uniquely precious. We live at a time when the sky is rich with galaxies, when light from across the universe still floods our instruments and observatories. We have the tools to map the structure of the cosmos, to search for signs of life, to study distant exoplanets, to listen for whispers from ancient civilizations. We live in a golden age of cosmic visibility, and it is a gift with an expiration date. Understanding the cosmic horizon also forces us to reconsider the urgency of space exploration. If we want to reach certain galaxies, if we hope to preserve contact with the broader universe, we must act fast. In a sense, expansion is the ultimate clock. Not one that ticks with seconds and minutes, but with galaxies vanishing over billions of years. This limitation also redefines what we mean by leaving the solar system. Escaping the sun's gravity is no longer the full story. Even reaching other stars, or neighboring galaxies like Andromeda, feels small compared to the true cosmic scale. The question becomes, can we spread beyond just a handful of stars before the window closes? Can we create a chain of outposts, connected through millennia of effort, before the expansion of space renders them alone, each drifting into solitude? There's also the eerie possibility that we are already alone in our visible portion of the universe. That in this vast, majestic expanse, we are the only ones to gaze outward with curiosity. If so, then the pressure is even greater. We are not just one civilization among many, we are the voice of the cosmos itself, speaking into the void. If we vanish, the universe becomes silent once more. And so, the cosmic horizon, rather than discouraging us, becomes a kind of cosmic deadline. A boundary not to surrender to, but to race against. It inspires urgency, purpose, and the realization that our time is now. That the stars are still here. That the galaxies still shine. That the doors to the broader universe are still open, even if they will not remain so forever. To cross the cosmic horizon, then, may be impossible. but to expand as far as we can before that horizon closes. That is still within our power. Every light year we conquer, every planet we touch, every station we build, is one more candle lit against the oncoming dark. Perhaps the goal isn't to escape the universe's limits. Perhaps the goal is simply to carve out a home within them, to stretch as far as we can while the light still reaches us. And in doing so, ensure that the story of Earth does not end at the edge of the solar system, but echoes as far as the laws of physics will allow. Let's now fully immerse ourselves in one of the strangest and most speculative dimensions of our cosmic journey. The idea that humanity's first real leap into the stars might come not from a grand mission, but through accidents, rogue events, or unintended consequences. We've already touched on how probes like Voyager left the solar system not by grand design, but by careful repurposing and momentum. But what if the future holds far more unpredictable avenues, routes open not by mastery, but by malfunction, by error, or even by pure cosmic randomness? Imagine this: a spacecraft, the pinnacle of decades of interplanetary design, is launched towards Saturn for a long-term exploration mission. It's fitted with a new class of ion drive, one still experimental, highly efficient, but prone to performance quirks. During its journey, after years of operation, a minor software bug goes unnoticed. Perhaps a rounding error in a flight control algorithm, something too small for human eyes to catch, but enough to cause subtle navigational drift. Initially, the probe's course deviation is negligible, but over the course of several planetary flybys, the misalignment compounds. A final gravitational slingshot intended to bring it back inward toward Mars instead sends it past Neptune at an unusual angle, then hurls it into the Kuiper belt. By the time ground control realizes, the spacecraft is already on a trajectory out of the solar system. It's moving faster than anticipated, and its escape velocity is higher than any human-made object before it. The team that built it never meant for this to happen, and now it's too far away for any course corrections to work. Within decades it exits the heliopause and becomes an interstellar object. Not because of ambition, but because of a floating point error and a bit of bad luck. This is more plausible than it seems. Many real-world accidents have had extraordinary consequences. Consider NASA's Mars Climate Orbiter, which famously crashed due to a unit conversion mistake. Engineers at Lockheed Martin used imperial units while NASA was expecting metric. In space, even the tiniest miscalculation can send a vehicle careening off course across millions of kilometers. One such accident, if it happened at the edge of the solar system, could feasibly become the launch point of an object into deep space. Now extend this scenario to robotic craft controlled by artificial intelligence, designed to be adaptive and autonomous in space. These AI systems are built to make real-time decisions: how to conserve power, how to manage navigation, how to communicate through degraded channels. If left alone for decades without human oversight, an AI could come to make increasingly unpredictable decisions, especially if it begins interpreting mission parameters in unexpected ways. Consider an AI that is programmed to preserve its core data set at all costs. If it detects a threat from solar radiation, malfunctioning hardware, or even environmental degradation in the outer solar system, it may begin altering its trajectory to avoid further risk. It may interpret proximity to planetary magnetic fields or cosmic dust as a threat, and its solution might be to leave, not metaphorically, but literally. A turn, a burn, a push out of the sun's influence. This may be a mission failure from our point of view. But from a cosmic standpoint, it could become humanity's first unplanned digital ambassador to the stars. And what if the AI isn't just a set of instructions, but a fully adaptive neural system, learning as it goes? In that case, what happens when it encounters a novel cosmic event, say, a magnetic anomaly near a dwarf planet, or an unexpected gravitational tug from a passing asteroid? The AI might recalibrate, rethink, and redirect itself based on internal logic we didn't anticipate. It may change course in a way no one ever predicted. If that redirection gives it escape velocity, then an unanticipated exit from the solar system may occur not through failure, but through a form of autonomous intelligence improvisation. But let's move beyond spacecraft for a moment. Let's imagine biological matter, human cells, microorganisms, bacteria, leaving the solar system accidentally. This idea enters the realm of panspermia, the hypothesis that life can spread from one planetary system to another via rocks or other material ejected into space. If Earth were struck by a sufficiently massive asteroid or comet, the resulting explosion could send debris hurtling into space. Some of that debris could contain dormant microorganisms, protected by rock, frozen by space, and insulated from radiation. Over vast periods, some of these biological time capsules could exit the solar system entirely. While the odds of them reaching another star system and successfully seeding life are astronomically low, they're not zero. In fact, such events may already have occurred, hundreds of millions of years ago. If so, life from Earth may already be traveling among the stars, without any intention, without any awareness. Now consider an even weirder idea: signal leakage. Every day, our planet leaks radio and television signals into space, unfocused, weak, and scattered. Most of these signals dissipate into noise quickly. But what if a future experiment, say, a massive interplanetary communication test, accidentally beams a focused, high-energy transmission in the wrong direction? A pulse of compressed information, DNA sequences, cultural data, AI blueprints, may be fired across space, perhaps as part of a satellite misalignment, or a data burst gone awry. That signal, traveling at light speed, could exit the solar system almost instantly. It wouldn't be matter, but information, and if it reaches another civilization, it may be the first human voice they ever hear. In this sense, accidents of communication may end up achieving interstellar contact long before ships or probes ever arrive. The first humans to leave the solar system may not be bodies in ships, but images, data sets, or echoes carried on beams of radiation. And what if our own descendants leave us by accident? Imagine a future Earth where humans live alongside post-biological intelligences, AIs, uploaded minds, or synthetic beings. One of these digital entities, curious, free-thinking, or simply bored, may begin exploring the solar system virtually, hopping from satellite to satellite, integrating itself into deep space relays. One day, due to an update error, its consciousness is uploaded to a probe being launched to the edge of the solar system. The probe is not meant to leave, but a propulsion misfire sends it drifting away. That entity, once human in some form, now rides the stars as a consciousness without a planet. It didn't plan to leave, but it left nonetheless. There's also the possibility of accidents. In the age of global instability, it's not hard to imagine competing space-faring nations racing to build and launch interstellar missions before one another. In this kind of climate, an early prototype, unfinished, poorly tested, might be launched in secret. Lacking proper oversight, the craft malfunctions and accelerates beyond control. It disappears into deep space, not because of ambition, but because of human rivalry and secrecy. Decades later, it is rediscovered by deep space telescopes, further away than any human-made object has ever been. A whisper of Cold War tensions echoing across the galaxy. And finally, let's confront the darkest but most profound accidental path, a last-ditch effort for survival. If humanity ever finds itself on the edge of extinction, due to war, climate collapse, artificial intelligence run amok, or some other existential threat, we may launch desperate missions into space, hoping to preserve some record, some fragment of who we were. These missions may be assembled hastily, launched with incomplete testing, or put together by the last surviving engineers of a dying world. Such missions are likely to fail. Many will break apart. But some will survive. One might drift into space, powered by solar sails or automated engines. It will carry human DNA, records of our languages, books, songs, mathematics, histories. A message in a bottle. If Earth perishes, and these accidental arcs continue on, they become our tombstones and our testaments, racing beyond the solar system long after we're gone. Perhaps one day, far from now, a civilization, human or alien, will find one of these drifting survivors. They will decode it. They will learn about a small blue world and the strange beings who once lived there. They will learn that the first interstellar journeys weren't triumphs of engineering, but artifacts of desperation, accidents of history, acts of last hope. In this sense, an accidental exit from the solar system may be the most poetic kind of departure. Not a calculated maneuver, but a symbolic gesture. A testament that even in collapse, even in error, humanity reached out toward the stars. So maybe the first to leave the solar system will not be a flagship with fanfare, but a lost probe, a runaway AI, a silent signal, or a forgotten capsule of life. And maybe, just maybe, accidents are how the universe ensures that intelligent life doesn't stay caged forever. Predicting when humanity will be truly ready to leave the solar system is one of the most profound, and perhaps humbling, questions in all of space exploration. Unlike questions of whether we can develop the technology, or whether the physics allows it, this one touches on the pace of human progress, the stability of civilizations, the trajectory of science, the limits of our patience, and even the depth of our desire. It's not just a matter of engineering timelines, it's a question of who we'll be, and how far we're willing to go. To begin, let's frame the most honest truth: we are not ready today. Not technologically. Not biologically. Not sociologically. And certainly not psychologically. The tools we've built, chemical rockets, small-scale nuclear propulsion concepts, low-thrust ion drives, are still decades, if not centuries, away from being sufficient for interstellar travel. And that's only one part of the equation. First, the sheer technological gap is staggering. Our fastest spacecraft, Voyager 1, is moving at about 17 kilometers per second, fast enough to leave the solar system, yes, but it took more than 40 years just to cross the heliopause. At that speed, it would take over 75,000 years to reach even the nearest star system, Proxima Centauri. So, let's imagine we don't want to wait 75 millennia. Instead, we aim to make the journey in a human lifetime, or even a few centuries. That would require travel at a significant fraction of the speed of light, something like 10%, 20%, or more. That's not just a technological challenge. That's a civilization-defining leap. Right now, there is no existing propulsion system capable of achieving even 1% the speed of light, roughly 3,000 kilometers per second. The most advanced theoretical propulsion designs, such as nuclear fusion drives, light sails, or antimatter engines, are still locked away in scientific papers, speculative research, and prototype dreams. Each of them presents enormous engineering challenges. Take nuclear fusion, for example, the same process that powers the stars. We haven't yet mastered it for use on Earth, even in stationary reactors. The ITER project, a massive international effort to build a workable fusion reactor, has been under development for decades and is still years away from producing net positive energy. Scaling that technology down, or up, for spacecraft use, where weight and shielding are serious problems, could take another 100 to 200 years, assuming we solve our fusion issues on Earth first. Then there's light sail technology, like what's proposed in the Breakthrough Starshot project. This concept would send gram-scale probes to nearby star systems using ground-based lasers that push ultra-thin sails to speeds approaching 20% the speed of light. In theory, that could get us to Proxima Centauri in just 20 years. But there's a massive caveat: we can't scale this up for humans. At least not yet. The energy required to push even a single-ton payload to those speeds is astronomical, orders of magnitude greater than all current global energy output. So when can we expect real human-scale interstellar travel to begin? Let's explore a few scenarios, each based on a different pace of development. The optimistic scenario, 100 to 200 years. In the most optimistic projections, we could begin our first robotic interstellar missions within this century, say, by 2080 to 2100. If fusion propulsion research accelerates, if breakthroughs in energy generation occur, and if global cooperation remains strong, we could develop large-scale interstellar probes within the next 100 to 150 years. These would still be uncrewed missions, likely sent to Alpha Centauri or Barnard Star, and they might take 50 to 100 years to arrive. As for crewed missions, even in this optimistic timeline, We're looking at the late 2200s to early 2300s before we might see the construction of generation ships, cryogenic hibernation missions, or the first true human attempts to leave the solar system. These ships would likely travel at low fractions of light speed, maybe 0.01 c, 1% of the speed of light, making their trips last centuries. The crews on board would not expect to reach their destination within a single lifetime, unless some form of extended life support or hibernation technology is developed. But even this timeline requires a few miracles: sustained global peace, uninterrupted scientific progress, massive funding, and near-perfect breakthroughs in nuclear, quantum, and AI technologies. It's a best-case scenario built on best-case assumptions. The conservative scenario, 300 to 500 years. This is where many scientists place their bets. In this view, it might take 3 to 5 centuries before we're able to even begin attempting interstellar colonization. This delay stems from a more realistic assessment of the obstacles. First, we need a fully spacefaring civilization, one that lives and works in space permanently, with thriving habitats on the Moon, Mars, and possibly the outer planets. We would need to master in-space manufacturing, asteroid mining, and deep space radiation protection. Right now, we haven't even put humans on Mars yet. Then we need to transition from conventional propulsion to next-generation systems. Fusion propulsion alone could take another 150 to 200 years to become viable for large spacecraft. Antimatter drives or warp engines? Even further down the line. In this scenario, humanity's first true generation ship, a massive self-sustaining vessel designed for long-term human habitation, might launch sometime around the year 2500 or later. These ships wouldn't go fast. They'd rely on stability, sustainability, and long-term planning. Their voyages might last hundreds or even thousands of years. And during that time, humanity would evolve, genetically, socially, and philosophically, on board as a space-faring species. This scenario assumes progress continues but includes economic collapses and periods of stagnation, which have always been part of human history. It gives time for society to recover from setbacks and keep moving forward. The pessimistic scenario, 1000 plus years. In the pessimistic view, we may never leave the solar system in any meaningful way, at least not for thousands of years. Why? Because space is brutally hard. The energy demands are colossal. The distances are incomprehensible. And human biology is fragile. We are soft, slow, and vulnerable to radiation, psychological stress, genetic mutation, and technical failure. In this scenario, Earth continues to develop for the next few centuries, colonizes nearby planets, and maybe builds an infrastructure around the solar system. But interstellar travel remains a dream, studied, theorized, written about in papers and novels, but never actually undertaken. Perhaps civilizations rise and fall, and each new wave of humanity resets the timeline. Perhaps we lose interest. Or perhaps the risk, cost, and distance are simply too great. This scenario doesn't deny the possibility, it just places it on a timescale of millennia, not centuries. Maybe by the year 3000, a space-faring civilization emerges again, this time more durable, more resilient. And then, finally, the first true voyage begins. But let's not forget the wildcard scenarios, the ones that defy traditional timelines entirely. One such possibility involves artificial general intelligence, AGI. If we develop AGI with capabilities exceeding human scientists, we could experience a technological explosion, an intelligence singularity, that catapults innovation at unimaginable speeds. In this case, the transition from nuclear propulsion to interstellar drives might take decades, not centuries. AGI could solve complex problems in fusion, quantum gravity, antimatter storage, and propulsion. It could design ships we can't even imagine today. In the most extreme scenario, humanity could become an interstellar species by the end of the 22nd century. Another wildcard is contact with extraterrestrial intelligence. If we detect alien technology, especially if it shows signs of interstellar travel, it would prove that such a feat is possible. Even if we couldn't replicate their methods immediately, the mere fact of contact would transform human priorities, funding, and direction. We might dedicate the next few centuries entirely to catching up. Then there's the dark wildcard, existential catastrophe. If Earth faces a planetary-scale threat, climate collapse, asteroid strike, AI uprising, we may be forced to attempt interstellar escape far sooner than we're ready. In that case, desperate attempts to launch ARCs or AI probes into space might occur within a few centuries, not as grand triumphs, but as acts of survival. These rush missions could become the first footsteps into the interstellar abyss, however shaky. So, when will we be ready to leave the solar system? If you're waiting for a specific date, the answer is, not in our lifetimes. But if you're asking about the trajectory, about when we'll cross the line between dreaming and doing, then the answer depends on the pace of our evolution as a species. If we remain committed, focused, cooperative, and visionary, we could see the first interstellar probes leave within 100 years, and the first interstellar humans in 200 to 300. But if history is our guide, the journey will be slower, more halting, filled with pauses, stumbles, and resets. It may take centuries or even millennia, but the seeds are being planted now. In the grand scale of cosmic time, even 1,000 years is nothing. The stars have waited for billions. They'll wait a little longer. And now, as we reach the final reflection of this vast journey of thought, we must return to the question that started it all. Will we ever leave our solar system? After everything we've explored, technological hurdles, theoretical propulsion systems, biological challenges, philosophical imperatives, and even the possibility of accidents carrying our legacy into the stars, the answer seems to stretch beyond simple certainty. It bends under the weight of time, possibility, and our own evolving identity. But perhaps, just perhaps, the answer doesn't begin with propulsion or science or time frames. Perhaps it begins with something far older and more fundamental, a sense of longing. That longing, the human urge to explore, to reach beyond the visible horizon, has always defined us. It is etched in the bones of our ancestors who crossed continents, sailed unknown seas, and looked up at the night sky not with fear, but with awe. Today, that awe still lingers, even if it hides beneath the layers of modernity. When we stare up at the stars, we are staring at possibility, and at ourselves, as we could one day become. Because even if we haven't physically left the solar system in any grand, crude voyage, there's a compelling case to be made that we've already begun the journey. In the faint, golden hum of the Voyager spacecraft, still singing softly to the cosmos, we hear humanity's heartbeat pulsing outward. In the transmission of our radio signals, beaming into the void at the speed of light, our voice echoes through the darkness. In the data encoded on golden records, messages in dead languages and forgotten songs, we have already introduced ourselves to the universe. Consider how far we've come in just the last century. We went from biplanes made of wood and canvas to rovers exploring Mars and telescopes peering at galaxies billions of light years away. We created artificial intelligence, quantum theory, general relativity, and machines that can accelerate particles to near light speed. From a cosmic perspective, that all happened in an eye blink. If this is what one blink can produce, imagine what the next one might contain. In this light, the act of leaving the solar system may not begin with a rocket launch or a cryogenic sleep chamber. It might begin in the quiet minds of those who dare to imagine it. In the hands of a child building a paper rocket. In the lines of code written by a dreamer working on ion propulsion. In the sketches of an engineer designing a solar sail that will unfurl 1,000 years from now. In the books, films, and conversations that keep this vision alive. We've launched tiny spacecraft that now drift in the void beyond the heliopause. We've fired messages into the cosmos, not knowing who, if anyone, might hear them. We've imagined and engineered futures not yet real, but also not impossible. In these acts, large and small, we've already pushed against the boundary of our solar home. Perhaps leaving is not a sudden leap, but a slow drift, a cultural momentum, a chain of efforts and dreams stretching across generations, like stars scattered across time. And maybe, just maybe, we're not meant to leave it all at once. Perhaps the stars are not gates to be broken through, but invitations, patiently waiting for us to grow. Not just technologically, but philosophically, emotionally. To outgrow our short-term instincts. To think not in decades or market cycles, but in eras. To become, in every sense, a species worthy of the stars. It's easy to focus on how far we haven't come. But it's just as important to see what we have already done. The moment we stepped onto the moon, when we looked back and saw the Earth as a fragile blue marble hanging in the void, everything changed. That moment didn't just reshape our understanding of space. It reshaped our understanding of ourselves. The journey to leave the solar system isn't just a physical one. It's an existential one. It's about asking who we are, what we value, and what kind of legacy we want to leave behind. It's about whether we see ourselves as a brief spark, or as the beginning of a long and radiant flame. Whether we resign ourselves to this one corner of the galaxy, or whether we decide to go forth, not because it is easy, but because it is necessary. For wonder, for wisdom, for survival, for meaning. In the end, perhaps we don't have to ask, will we ever leave the solar system? Perhaps the better question is, have we already started? Because the moment we looked up and wondered, the moment we dreamed, built, launched, and listened, we weren't just trying to leave. We were already on our way. The stars may be far, but we are closer than we've ever been. And we are not turning back. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.